All specialists studying comets agree. The behavior of this interstellar object, designated as the third interstellar flying rock, completely exceeds all their previous observations and knowledge. As this mysterious cosmic wanderer approaches its October close encounter with Mars, it began to exhibit unusual signs that literally shook the entire scientific community. In particular, it started forming a bright, intense green atmosphere that expands and extends far beyond the diameter of the largest of the gas giants, Jupiter. The size of this expanding shell is impressive in its scale. Moreover, the object's brightness fluctuates sharply, sometimes increasing suddenly, sometimes dropping unexpectedly, creating a jumpy effect as if someone is controlling its luminosity through a mysterious mechanism. The tail of this celestial body contradicts all known laws of solar physics. Its structure, direction, and properties astonish even the most experienced astronomers. The dust scattered around it disperses sunlight in such a way that its appearance gives the impression of something artificial, as if it were the result of unknown technologies or technologies beyond our understanding. The closer it gets to the red planet, the more obvious it becomes that its appearance and properties evoke a sense of unnaturalness rather than that of a natural cosmic object. But what is truly strange and perhaps the most mysterious, is what almost no one talks about aloud. While astronomers worldwide, as well as amateur astronomers, fill social networks with preliminary images of this cosmic phenomenon, all major powerful space telescopes, such as Hubble, James Webb, and Gemini, have remained silent since August. This silent spectacle raises more and more questions. Stay with me until the very end of this nocturnal immersion to understand why the third interstellar rock behaves so strangely and what is hidden behind the silence of official structures. Because right now, it seems, one of the most important celestial events of the 21st century is unfolding. The introductory part of this story is about a comet that refuses to follow the usual rules. In mid-September 2025, events occurred that seemed impossible and even fantastic. Suddenly, without apparent reason, the third interstellar flying rock became brighter than all existing models predicted, and this happened at a point when it approached approximately 2 astronomical units from the Sun, that is, quite close in cosmic terms. The question that troubles astronomers and causes them many concerns is very simple, yet also very important. Why is this object exhibiting such unusual behavior? To understand the scale of this astonishment, it is worth briefly explaining what the predicted brightness curve means in terms of human perception. This can be likened to a cosmic weather forecast, except instead of rain or sunshine, astronomers predict how bright a particular object will become as it approaches our star. These predictions are not random guesses or assumptions. They are based on decades of comet observations, complex models explaining how ice sublimates in the vacuum of space, and a thorough understanding of how dust particles scatter sunlight. Over the course of several weeks, as Comet Atlas approached the Sun, its brightness increased according to a pre-calculated scenario. This entire process was monitored by both professional and amateur astronomers around the world, all observing a steady rise in its brightness as it moved inward into the solar system. These measurements matched the expected values. The closer the object got to the Sun, the more it heated up, releasing increasing amounts of gas and dust, which in turn created its characteristic diffuse atmosphere. However, everything changed between September 7th and September 15th. During this period, observers began to record deviations from the expected scenario. Currently, discussions are actively ongoing within the astronomical community regarding the nature of the observed increase in brightness of this interstellar object. Many are questioning whether this is a sudden burst of comet activity or if it is a more familiar phenomenon known as the aperture effect. This concept describes a situation where brightness measurements can be distorted depending on the size of the telescope and the data collection methods used. Imagine this scenario. You try to measure the size of a campfire burning in the distance. If you squint and look through a narrow tube, similar to a small aperture telescope, your perception will be limited to only the brightest tongues of flame, giving the impression that the fire is small but very bright. However, if you open your eyes wide and look across a broader area, you'll find that the flames occupy a much larger space, and the flickering and light spread far beyond initial expectations. Similarly, differences in telescope sizes and observation techniques can lead to such distortions in brightness measurements of a comet, especially if its atmosphere is diffuse and heterogeneous. These discrepancies are also evident in the data collected in the Comet Observation Database, which is widely used by professional astronomers for analysis and comparison. The data clearly show that the brightness variation graphs display an upward trend that suddenly becomes noticeably steeper in mid-September. This slope undoubtedly indicates significant changes in the object's properties, although the interpretation of this fact remains a subject of debate. To understand the scale of the processes underway, it is essential to pay attention to the comet's velocity. As it approaches the Sun, it moves at a speed exceeding 20,000 km per hour, specifically about 210,000 km per hour. This pace allows it to cross an entire continent in less than a minute, demonstrating the incredible velocity of this cosmic visitor. Near the point called perihelion, the closest point of its orbit to the Sun, media reports indicate that its speed reaches approximately 68 km per second. Given these figures, the exact time when the comet will pass through perihelion has been precisely calculated. It will occur at the end of October, more specifically between the 29th and 30th, at a distance of roughly 16 to 1 astronomical unit from the Sun. For comparison, this is just inside Mars' orbit, which is very close in astronomical terms. Speaking of Mars, it is worth noting that the interstellar object designated as 3I ATL will approach the red planet on October 3, at a distance of about 0.19 astronomical units. This close approach has attracted particular attention from specialists, as it coincides with planned operations and missions orbiting Mars. As part of these studies, modern high-resolution visualization systems are expected to be used, such as the high-rise camera, designed to capture detailed images of the planet's surface, as well as systems for color and stereoscopic imaging of the surface, known as CAS, and the High-Precision Stereoscopic Camera HRSC. These tools enable scientists to obtain the most accurate and detailed information about this interstellar visitor's appearance, movement, and properties. So, what is ultimately happening in the distant cosmos, high above our heads? The answer to this question seems quite simple, yet its implications could be rather alarming. Either this interstellar object, referred to as 3I ATL, is releasing additional gas and dust that our current models and theories did not predict, or our instruments are detecting the presence of a very large and complex atmosphere around the comet, which, in turn, misleads our calculations and interpretations. It is possible that both factors are occurring simultaneously, and the consequences of this actual collision could be significant. Unlike typical comets, which originate in the Kuiper belt or the Oort cloud and follow predictable orbits around our Sun, the so-called object designated as 3I ATL originated from a completely different place, interstellar space beyond our solar system. Its behavior was expected to provide valuable insights into the composition and properties of objects coming from other star systems, as such interstellar visitors represent a unique source of information about matter between stars. However, despite our expectations, this object refuses to follow the laws and models that have guided comet observations for over a century, behaving in a completely different manner. The anomaly associated with the sudden increase in brightness of this object suggests that our understanding of interstellar visitors remains painfully incomplete and fragmented. The question arises: are we missing the most crucial aspects of the behavior of such celestial bodies? Perhaps comets from other systems operate under entirely different laws than those we are accustomed to observing in our familiar objects, and their mechanisms of interaction with the environment differ significantly. The era we live in seems more exciting and intriguing than ever. As the 3I Atlas approach their closest point to the Sun, all telescopes on Earth and in space are anxiously preparing for a thorough study of this guest from interstellar space. What they discover in the coming weeks could completely overturn our notions about the nature of objects in the spaces between stars, expanding the horizons of our understanding of the origins and evolution of cosmic bodies. However, the brightness surge anomaly is only the first sign that the behavior of the 3I Atlas is not limited to mere oddity. The focus is on a fuzzy shell surrounding its core, which, like a living organism, rapidly expands and swells to astonishing sizes, surpassing many planets in scale. This expansion occurs faster than current physical laws predict, raising serious questions and challenging our fundamental ideas about the mechanisms of comet activity. To grasp how significant this is, we need to understand what a coma is, the subject constantly discussed by astronomers. Imagine a comet's atmosphere as a volatile and chaotic mixture of gas, dust, and plasma extending hundreds of thousands of kilometers into space. Unlike Earth's atmosphere, which is a relatively stable and gravitationally bound shell of air, the coma is a dynamic, ever-changing environment formed under the influence of surface heating and sublimation of ice, when solid material transforms directly into gas. This process releases dust particles into space, creating a vast, fluffy cocoon that can surpass the size of some planets. Then, on August 6, 2025, the James Webb Space Telescope, equipped with its powerful infrared instruments, directed its gaze at the object named 3I Atlas and detected something entirely unusual and unexpected in its coma. Within this cloud of gas and dust, an anomalously high concentration of carbon dioxide was recorded, immediately drawing special attention. Compared to water vapor, which usually dominates in comets, the presence of such a large amount of carbon dioxide indicates that this interstellar comet formed under extremely cold conditions, either in the region of its native star system or through a very unusual chemical evolution, different from that typical of familiar comets. Why is this so important? Because water ice requires significant solar heating for sublimation, whereas carbon dioxide begins to turn into gas at much lower temperatures, meaning much farther from the Sun. This suggests that the Third Eye Atlas became active much earlier than is typical for comets. Further studies, conducted using near-infrared spectroscopy, revealed an extremely expanding shell primarily composed of carbon dioxide. This shell extends hundreds of thousands of kilometers into interstellar space, creating an impressive and mysterious phenomenon. Preliminary estimates suggest its extent reaches approximately 700,000 kilometers, roughly twice the diameter of the Sun's disk. However, it is important to emphasize that this figure is more of an approximation rather than an absolute scientific fact, as observational methods and analytical approaches can yield varying results and interpretations. One significant detail was recorded during a filming session conducted on July 21 using a space telescope. These observations added another piece to the overall picture of this enigmatic object. During the investigation, a compact core was discovered, completely hidden behind a bright dust cocoon. Using brightness and light characteristic modeling methods, astronomers were able to determine an upper limit for the radius of this core, which does not exceed approximately 2.5 kilometers. This discovery contradicts the widespread claims on social media and some news sources about the giant size of this object. Additional confirmation was obtained from data collected as part of the Legacy Survey of Space and Time project, carried out by the Vera Rubin Observatory. These observations, made in June, provided further information allowing the core's size to be estimated within a few kilometers across. Some news reports indicate diameters ranging from 3 to 5 kilometers, but scientists emphasize that all these estimates are accompanied by significant uncertainty. As a result, the final size remains within a range rather than a precise figure, and these numbers should be regarded as approximate. Understanding the nature of the expanding shell, designated as 3IATL, requires an understanding of the concept of dust plasma. In simplified terms, this is a mixture of neutral atomic particles and gas molecules, some of which are ionized under the influence of solar radiation. Such ionized material does not behave like ordinary matter. Instead, it organizes itself into complex structures, forming threads and layered formations that can pulse, shift, and take on organ-like shapes. When observers record visions of living patterns within the comet's coma, they are actually witnessing the manifestation of fundamental self-organization processes in plasma. Magnetic fields permeating the ionized gas create invisible magnetic pathways along which charged particles move. As a result, intricate structures emerge, which can be captured in high-resolution images. These patterns are formed according to the same physical laws that govern the auroras, bright, dancing plasma loops that spread across polar skies and occur high in planetary atmospheres. It is these similar processes that create the complex and astonishing patterns, giving the impression of lively dynamics in cosmic phenomena. What makes the situation even more perplexing and intriguing is the combination of a massive, rapidly expanding comet rich in carbon dioxide with the unique characteristics of an interstellar object. The first interstellar object, known as Oumuamua, showed no obvious signs of cometary activity. In contrast, the second object, Borisov, behaved like a typical comet found in our solar system. The third object, designated Triatlas, occupies an intermediate position between these two extremes. It exhibits clear signs of a cometary nature, yet possesses chemical and physical properties that do not fully align with our expectations of how a carbon dioxide-rich comet should behave under conditions of rapid expansion and unusual brightness evolution. Overall, this object challenges existing categories and notions of interstellar bodies. Its unique features, such as the rate at which the comet itself is growing, seem to raise a host of fundamental questions posed to modern astronomers and space researchers. Primarily, this concerns the fact that, based on the known laws of solar heating received by the object called Triatlas, located at its current distance from the Sun, and considering the sublimation rates of various types of ices in its shell, one might assume that the expansion of this cometary body should proceed according to fairly predictable models. These models suggest that the comet's shell, under the influence of solar heat, gradually and uniformly evaporates, and its expansion is driven precisely by this process. However, observing the actual changes in Triatlas's behavior reveals a completely different picture. The comet's development occurs much faster than the predictions of standard models allow. It is as if there is some additional energy source stimulating the sublimation process, making it more intense and rapid. The question arises, what could this be? Could the interior of a comet, despite its small diameter, experience heating due to radioactive decay? Probably not, since the size of the comet is too small for this to have a noticeable effect. Or perhaps, the rotation of Trialis occurs at such a speed that it creates significant stresses within its structure, cracking the surface and exposing fresh ice, which in turn increases activity. Such a scenario is possible, although to date it has not been confirmed through experiments or observations. Finally, there is a hypothesis about an unusual composition of the comet, which includes volatile substances not found on Earth in similar concentrations or in such forms that could explain its unusual behavior. An important role in these mysteries is played by the plasma component. The solar wind, a constant stream of charged particles emanating from our star, interacts with the expanding coma of Trialis. This interaction causes the formation of a shock wave, similar to the wake left by a boat moving through water. Such an encounter can accelerate the comet's expansion and lead to the formation of filamentary structures, giving the comet an almost living and dynamic appearance. However, even considering these effects related to the plasma component, the growth rate still seems extraordinarily high. It can be said that Trialis appears to operate according to laws different from those we are accustomed to observing in other comets studied over the centuries. The explanation for part of this phenomenon lies in carbon dioxide chemistry, but it cannot fully account for the entire complexity of what is happening. As it approaches the inner solar system, each new observation of this interstellar visitor raises more questions than answers. The comet's shell continues to expand, fueled by sublimating ices, which seemingly should not be so active at such a close distance to the Sun. But expansion is far from the only mysterious aspect of Trialis's behavior. During observations conducted by astronomers over the summer months, an even more astonishing phenomenon was observed. The comet's color began to change hue, acquiring a sinister green glow that any science fiction director could use in their fantastical scenarios. The second part of this story is dedicated specifically to this unusual green glow. On a clear, cloudless night, when the sky was particularly dark, over the Namibian desert during the eclipse period from September 7th to 17th, astronomers and amateur observers documented this extraordinary event. Their photographs clearly showed that Trialis was glowing with an extraordinary green hue, which could not be mistaken for any other. Its brightness and saturation appeared so intense that it gave the impression that the light was emanating from an artificial source rather than a natural object. Green glows in comets are not entirely unprecedented in astronomy. This phenomenon occurs when carbon molecules, especially diatomic molecules, are present. As the comet slowly approached the solar system, noticeable changes took place in its appearance and chemical composition. The increasing radius of solar radiation reaching its surface gradually heated its core and the surrounding gaseous envelope. This process led to the breakdown of complex organic molecules containing carbon in their structures under the influence of high temperatures and solar ultraviolet radiation, resulting in simpler compounds. One of the key products of this decomposition was diatomic carbon, a molecule capable of emitting characteristic green fluorescence when excited, which was observed in the comet. The intensity of this fluorescence directly depended on both the amount of solar radiation hitting the comet and the volume of carbon-containing substances present in its composition. According to classical models, the more sunlight and the richer the comet was in carbon compounds, the brighter and more noticeable its green glow should have been. However, in the case of the comet known as 3I Atlas, observations revealed a completely different scenario, surprising scientists and becoming the subject of active research. Initial spectroscopic studies of this object showed that it was extraordinarily rich in carbon dioxide, which seemed logical given its pronounced activity. At the same time, more detailed analysis revealed that its composition exhibited very limited signs of classical carbon chemistry, which is usually associated with the formation of green fluorescence. This combination, a high concentration of carbon dioxide alongside weak or absent characteristic carbon fluorescence, caused confusion among specialists. According to existing models, such a composition should have resulted in either very faint or completely absent green glow. Yet, in reality, the observed data indicated that the green fluorescence of Comet 3I Atlas manifested with extraordinary strength and at very early stages of its approach to the Sun, much earlier and more intensely than predicted based on its chemical composition and distance from the star. This discrepancy between theory and observation seemed astonishing, and scientists acknowledged that it required further investigation and explanation. It was also surprising that the comet began to glow green earlier than expected, and that its fluorescence was much more intense than what would be expected based on its abundance of carbon dioxide. All this pointed to the existence of something unusual in its chemical behavior and response to solar heat. An important aspect became the need to understand why this was happening, since the process is based on a delicate and complex balance of chemical reactions within the comet, occurring in its coma. As the comet approaches the Sun and its temperature rises, various volatile substances sublimated, that is, transitioned directly from solid or liquid states into gas. Moreover, different components responded differently. For example, water ice required a significant amount of heating to begin sublimating, while carbon dioxide turned into gas slightly earlier, at a lower temperature. At the same time, complex carbon molecules broke down into simpler compounds at various stages of this process. All of this created a dynamic chemical scene, in which carbon-containing molecules decomposed and formed new chemical compounds capable of fluorescing under the influence of solar ultraviolet radiation. Interestingly, the green glow indicated that these molecules were not merely breaking apart but also being excited by solar radiation, emitting light in the process. However, the timing of this phenomenon, occurring much earlier than predicted by existing models, suggested that there was something unusual about the comet's chemical behavior. It can be hypothesized that Comet 3I Atlas contains a unique type of carbon compounds or structures that we have not encountered before. When the comet plunges into a denser atmosphere due to the accumulation of gas and dust, this leads to changes in its appearance and physical characteristics. In particular, the increase in the density of the coma, caused by the release of gases and particles, becomes noticeable. Under such conditions, complex chemical reactions begin to occur inside the comet, and some molecules, such as diatomic carbon, become more prevalent and active. This very fact contributes to the enhanced green glow sometimes observed in comets. It can be said that these two phenomena, the growth of the coma and the intensification of the green glow, are essentially manifestations of the same fundamental process related to chemical and physical transformations occurring in the comet's atmosphere under the influence of solar radiation. Imagine neon signs that light up when an electric current passes through them. Such luminescence results from processes occurring inside the lamps. Similarly, the green luminous glow we observe in a comet indicates that accelerated reactions are taking place within its composition and chemistry, often faster than previously assumed. This acceleration is driven by solar radiation energy, which, acting on the substances inside the comet, causes their more intense transformation. As a result, reactions once considered slow or insignificant can speed up, leading to a brighter and more saturated green glow. However, when examining visual images captured with modern digital cameras and processing techniques, it is important to remember the need for caution. These technological tools are capable of enhancing the colors and brightness of images beyond what the human eye would see directly. For example, photographs of green luminescence on the internet can appear so vivid and saturated that it creates the impression that a comet is shining brighter than it actually is. However, there is a spectroscopic line at a wavelength of 1308 nanometers that confirms the physical nature of this phenomenon. This line corresponds to the fluorescence of diatomic carbon, indicating its actual participation in the processes within the comet and confirming that the green glow is not merely an illusion but the result of specific chemical reactions. Moreover, the green luminescence serves as an important tool for understanding the internal structure and rotation of the comet. If we assume that the comet, or more specifically its nucleus, rotates sufficiently quickly, say, within a few hours, then different areas of its surface would be subjected to repeated solar heating. As a result, changes would occur in the chemical composition and activity of these regions, which in turn would influence the intensity and distribution of the green fluorescent glow. Some observers have noted that over the course of several hours or days, the brightness and scale of the green color fluctuated, indicating that the comet's nucleus likely rotates and does so quite rapidly. These slight changes help scientists understand the internal structure of the comet and how it responds to sunlight. It is also important not to underestimate the psychological impact of bright green luminescence. Throughout human history, unusual celestial phenomena have evoked both awe and fear, especially when it involved comets with a pronounced green hue, which often appeared from interstellar space or seemed unusual and alien. In culture and mythology, such phenomena were frequently associated with the supernatural or the otherworldly, provoking fear and wonder. In the era of scientific progress, we tend to interpret these phenomena through the lens of knowledge, and science fiction has long linked green glow with extraterrestrial technologies or alien civilizations. However, science shows that nature is capable of creating phenomena more astonishing and strange than even the most daring imaginations of writers. The green glow we observe in a comet, although it appears unusual in terms of timing and intensity, is a quite real physical consequence of chemical processes occurring under the extreme conditions of space. A comet, in essence, is a natural laboratory where materials brought from space are subjected to various reactions, making it perhaps the most striking and unusual astronomical phenomenon for an observer. Combined with the rapid expansion of the coma and its unusual darkening, the green glow, which appears extraterrestrial and mystical, creates the impression for the viewer that something entirely uncharacteristic of typical images of space is happening before their eyes. This bright, slightly flickering glow evokes admiration and wonder. However, even it pales in comparison to one very important and mysterious feature that makes astronomers scratch their heads and work on its unraveling almost overtime. This is the unusual orientation of the tail of Comet Triatlas, which seems to contradict the fundamental laws of physics operating within our solar system. In the classical understanding of comets, their tails point away from the sun, like cosmic flags fluttering under the influence of solar wind and solar radiation. This principle has long been the basis for understanding the nature of comets, solar radiation, possessing immense energy, and the stream of charged particles emanating from our star at hundreds of kilometers per second, create two characteristic tails. The first, the dust tail, bends and follows the comet's orbit, as the pressure of solar radiation pushes dust particles away from the nucleus. forming an arched curve reminiscent of a cosmic wind billowing behind a moving object. The second, the ion or plasma tail, is a stream of charged particles that ionize molecules and dust around the comet, moving strictly in a direction directly away from the Sun, as the solar wind carries them in the opposite direction. It is precisely because of this combination of two types of tails, created by different forces, that the recognizable, bright, and spectacular image of a comet is formed, which we are accustomed to seeing. The physics of this process is simple and clear. Particles, dust, and ionized gas move along paths that offer the least resistance, created by solar forces, solar radiation and solar wind. All their movements obey the laws of physics, and these forces determine the direction and shape of the tails. In most cases, the observed effect is exactly that. Particles and gas, subject to these forces, move away from the nucleus, forming a characteristic arc-shaped structure. However, initial observations of comet Triatlas revealed something that fundamentally contradicts these established notions. Instead of material moving away from the Sun, as is usual, astronomers saw a stream directed straight toward our star. This was called an anti-tail. In this context, it seemed as though dust and gas particles were being ejected not away from the Sun, but toward it, as if the comet somehow defies the laws of solar wind and radiation pressure, as if it itself somehow gives the order to move against the flow. Before immediately assuming mysterious causes for this phenomenon, such as anti-gravity or the existence of alien propulsion systems, it is worth understanding that anti-tails, despite their rarity and visually impressive complexity, have a fully scientific and natural explanation. They occur as a result of the unique combination of three-dimensional observation geometry and the structures of dust, gas, and ionized particles surrounding the comet's nucleus. Imagine looking at a thin layer of dust particles in space. If this layer extends both toward and away from the Sun, and you observe it from a certain angle, then the part of the layer facing the Sun may appear projected onto the sky. This creates an optical illusion that the material is moving toward the Sun, even though it may actually be receding from it. This effect is purely due to the geometry of sight, not any unusual physical contradiction. The geometric complexity increases when considering the comet's orbital parameters, such as the inclination of its orbit, its velocity, and the angle of its movement. The comet currently observed in the sky follows a very unusual, and in some ways even mysterious, trajectory. Its path is almost retrograde, meaning it moves in nearly the opposite direction to the typical motion of objects in our solar system. Additionally, its orbital inclination relative to the plane of the ecliptic is about 5 degrees, which is relatively small but still sufficient to significantly influence how this celestial body is perceived from Earth. This plane is the one along which most planets orbit the Sun, and it is in this zone that the main movement of our planets occurs. However, the comet's inclination and its unusual trajectory create unique conditions for observing and interpreting various effects that may seem strange or even mystical to observers on Earth. These conditions undoubtedly enhance the potential for the appearance of unusual perspective effects, visual illusions or optical phenomena that are difficult to explain within the framework of standard comet behavior models. Later, as observations continued, particularly after an impressive photograph taken by the Gemini South Telescope on August 27, it became clear that the comet had begun to develop a more typical tail, directed away from the Sun. This anti-solar tail is a classic feature of comets, which forms when gas and dust particles ejected from the nucleus are pushed by solar wind and ultraviolet radiation from the Sun, creating a long, bright stream extending in the opposite direction of the star. Such a tail usually resembles a glowing line stretching away from the Sun. However, what is especially interesting is that, prior to the appearance of this normal tail, a stream directed toward the Sun, opposite to the usual direction of the solar wind, was observed. This stream attracted special attention from scientists and observers, sparking hypotheses about the unusual nature of the comet, its structure, and behavior. To gain a deeper understanding, a modern and precise method called polarimetry was employed, a technique that allows the study of the orientation and properties of light waves scattered by tiny particles of dust and gas surrounding the comet's nucleus. During these measurements, a complex tail structure was revealed, which does not fit into conventional models. In particular, the analysis of the polarization of light scattered by dust and plasma uncovered organized and structured distributions of these substances, markedly different from the simple, spherical, or elongated shapes typical of most known comets. These observations indicate that both the gas and dust surrounding the comet's nucleus are organized in a much more complex and diverse manner than classical models suggest. One can imagine the difference between a perfectly smooth sphere and a complex, multi-layered origami fold. Both are made of the same material, but their structure and internal configuration are entirely different. All of this, the anti-tail, the unusual flow of substances, and the intricate structure, created a spectacle that is hard to ignore. It evoked a natural sense of wonder and suspicion among observers, as such phenomena seem to challenge the fundamental laws of physics governing the movement and behavior of celestial bodies. For skywatchers, these phenomena appear not just unusual but evoke associations with something supernatural or even mystical, as if the laws of nature momentarily manifest differently than usual. This apparent abnormality in behavior, the possibility that the comet somehow opposes the solar wind, tempts many to seek more exotic explanations. Perhaps it is not an ordinary cosmic body at all, but something with its own internal force, capable of moving independently and changing its trajectory. However, in astronomy, the reality is often much more subtle and complex than such hypotheses suggest. That is why, despite the impressive visual effects and speculations about the comet's unusual nature, the true cause of its behavior most likely lies elsewhere. What initially appears to be a tail directed toward the sun may actually be a complex combination of materials moving in multiple directions simultaneously. From our specific vantage point, we can only see individual components of this phenomenon, as observing from a single angle limits our perception of the entire intricate picture. To fully understand the nature of the comet's anti-tail, one must employ three-dimensional thinking, imagining the space and volume, since two-dimensional images are merely projections of three-dimensional reality. This process can be compared to how a person observes shadows cast on a wall and tries to determine the shape and orientation of the objects creating those shadows. Shadows provide us with important information, but correctly interpreting their form and position requires an understanding of the geometry and lighting involved. As Comet Atlas continues to approach its perihelion, the closest point of its orbit around the Sun, its anti-tail is likely to evolve and change. Different viewing angles allow observers to see or, conversely, hide certain parts of the comet's extended atmosphere, contributing to new visual effects and unexpected geometric surprises. For astronomers, this presents a particular challenge. They must distinguish true physical anomalies, caused by the actual properties of the object, from apparent oddities that arise due to observational features related to perspective and vantage point. The comet's anti-tail serves as a vivid example of how the appearance of a celestial body can seem alien and even incredible, although everything occurring adheres to lawful physical principles. The unusual external appearance of this comet results from a unique combination of chemical and physical characteristics, accompanied by complex observation geometry that, like a magnifying glass, amplifies perceived oddities and mysteries. However, it is precisely the geometry and the effect of perspective that give way to another aspect, one that prompts scientists to use words like unprecedented and anomalous. The feature related to how this comet polarizes light allows the detection of characteristics previously unseen in any object within our solar system, and even beyond. This discovery sparks genuine interest and adds new knowledge to the field of astronomy. Moving on to the next aspect, the sky full of unexpected phenomena. The autumn of 2025 transformed the night sky into something resembling a cosmic jam or a dense mass of moving objects. Several bright comets appeared simultaneously, piercing through the inner regions of the solar system, creating a spectacle that had not been visible to the naked eye in many years of observation. It was a true stellar carnival, akin to a rare and bright event, unique in its scale. At the center of this celestial show is Comet Atlas, which seems to have come from another world, from beyond the boundaries of our solar system, like a guest from another star system, surrounded by numerous auxiliary comets that, apparently, formed much closer to Earth than the Sun. The timing of these approaches created an astonishing coincidence. Many cosmic events occurred almost simultaneously, creating something akin to cosmic merging. Specifically, comet R2S reached its closest point to the Sun on September 12, and by October 20, it approached Earth to a distance of approximately 0.25 astronomical units, which is about 23 million miles. This distance is small enough on an astronomical scale for the comet to become visible to the naked eye under good night sky conditions. At the same time, Comet 414P, Stereo, a periodic comet that returns to the inner regions of the Solar System every 7 years, reached its perihelion on September 27. At that time, it was approximately 0.2 astronomical units from the Sun. In the coming weeks and months, a new comet is expected to appear in the sky, reaching its perihelion on November 8. On that day, it will be about 0.53 astronomical units from the Sun, which, under certain conditions, will allow observers, even in areas with moderate light pollution, to see it with the naked eye. This event provides a wonderful opportunity to understand why multiple comets sometimes appear simultaneously in the sky without being physically or cosmically connected. Imagine long highways diverging from different points but all leading to the same large city. Similarly, comets move along different orbits, following their unique trajectories, which ultimately bring them through the inner regions of the Solar System at roughly the same time. As a result, it may seem as though these objects are somehow coordinated or linked, but in reality, their simultaneous appearance is merely a coincidence arising from the characteristics of orbital mechanics and our observational perspective from Earth. The visual clustering of bright comets is the result of this combination of orbital paths and the fact that we, as observers, see them at specific moments when they approach the inner solar system, developing bright comas and long tails. Moreover, comets become noticeable to us only when they are located in parts of the sky where lighting conditions allow for good visibility, usually in dark areas free from city light pollution. Therefore, the appearance of several bright comets in the sky at once is more a statistical pattern related to the nature of comet orbits and our perception than a consequence of any physical interactions between them. In other words, their simultaneous appearance is not a sign that they are somehow connected or interacting, but merely a reflection of natural laws and the characteristics of their orbital paths. But comets are not the only celestial objects that delight the eye and attract attention during this autumn season. In recent weeks, there have been other interesting events in the sky that have further intensified the sense of activity and richness in space. A particularly noticeable wave of events has been associated with the close approaches of various asteroids to our planet. In mid-September, several such cases occurred simultaneously, each attracting media attention and sparking numerous discussions on social networks. The most prominent of these was the passage of an asteroid designated 25FA22, which took place on September 18. Although this asteroid flew past at a distance of several million kilometers, a completely safe distance and posing no threat to Earth, its approach sparked a wave of interest. The media actively covered the event, and social networks buzzed with discussions about potential consequences and scenarios related to such objects. The name of this asteroid, seemingly chosen to evoke associations with the upcoming year, 2025, along with its activity during the same period as the peak comet activity, created a special atmosphere of heightened vigilance and concern regarding the surrounding cosmic objects. During this brief period, other asteroids were also observed, each making its own relatively safe close pass by Earth. Each of them drew attention and became a topic of discussion, giving the impression that September of this year was particularly eventful for those monitoring near-Earth objects. However, in reality, the situation is much more mundane. Such asteroids regularly pass relatively close to Earth, and most of these events go unnoticed or do not attract significant public interest. The high level of attention to these events is more a result of modern detection and observation capabilities. Today's telescopes and automated systems allow us to track even very small objects approaching our planet, often days or even hours before their closest approach. Therefore, it may seem that such unusual events are becoming more frequent, but in studying celestial phenomena, there is often a tendency to identify patterns, attempt to trace causal relationships, or predict developments based on observable signs. This trend is especially evident when analyzing various astronomical phenomena, from comet appearances to the movement of planets and other space objects. Throughout history, humanity has perceived unusual configurations related to celestial bodies as signs of fate, omens, or messages sent by higher powers or other forces of nature. These interpretations often gain significant importance, becoming part of cultural and religious beliefs, and sometimes serving as causes for mass panic or grand celebrations. In the modern world, with sufficiently advanced astronomical technology and observational capabilities, the number of registered comets, asteroids, and other celestial objects has significantly increased. Naturally, this elicits new psychological reactions among people, especially those prone to more fanciful or exotic hypotheses. The timing of various astronomical phenomena, their cyclic nature, and unusual features generate many questions that often go beyond conventional scientific explanations. If we assume that an advanced civilization with cutting-edge technology might be interested in hiding its reconnaissance missions in space, logic suggests that such devices observing our solar system would carefully disguise themselves as natural cosmic phenomena. For example, they might coordinate the arrival of their satellites so that they appear among numerous comets passing near the Sun. This approach would allow covert observation without attracting attention or arousing suspicion among astronomers and researchers. The idea that artificial objects could blend into a crowd of natural celestial bodies seems quite plausible and effective. Especially since periodic clusters of comets occur in our solar system, caused by gravitational disturbances at the system's edges, such as in the regions of the outer planets' orbits and beyond. During these periods, a vast number of objects, previously far from the inner system, suddenly begin approaching the Sun. This happens because gravitational interactions, for instance with Jupiter or other large planets, can eject comets onto trajectories that intersect with the inner system. All these comets passing through at the same time create natural clusters resembling cosmic swarms. In such cases, if among these bodies there are artificial satellites or reconnaissance probes, they could easily blend in with the natural comet group, becoming invisible to observers. Without detailed analysis and specialized differentiation methods, these objects might remain unnoticed, as their trajectories and characteristics do not raise particular suspicion against the backdrop of natural processes. Current events related to the appearance of new objects generate even greater interest, especially considering that some trajectories and features make them particularly attractive for reconnaissance or research missions. For example, a trajectory passing close to several planets could serve as a universal route for studying various worlds within a single expedition. Let's consider, for example, a celestial object known as the three asteroids, or sometimes referred to as tri-asteroids. It moves along an orbit that passes very close to Mars, allowing detailed observations of this planet during its approach, and then continuing inward toward the Sun, collecting data about its internal structure and atmosphere. From a strategic and tactical perspective, the current period can be considered particularly favorable for covert observations. The abundance of bright astronomical phenomena and widespread cometary outbursts creates an excellent backdrop for disguising any unusual activity. The sky is constantly filled with numerous bright objects, and any unusual anomaly or unidentified object can be easily overlooked. The question regarding the nature of the mysterious object recently discovered is becoming increasingly urgent and relevant, especially when it concerns the latest information that casts serious doubt on its explanation within the framework of conventional scientific understanding. The way the trio of asteroids, designated as Tri-Atlas, polarizes light by reflecting sunlight back to Earth demonstrates such unusual and astonishing characteristics that many space scientists struggle to find natural causes capable of fully explaining what they observe. This issue prompts deep reflection on the nature of this object and poses a challenge for researchers to determine whether they are dealing with a natural phenomenon or the result of something artificial, created by an intelligent civilization or other conscious intervention. The discussion of this topic becomes particularly acute when we turn to the so-called interstellar visitors, objects that, for the first time in observational history, have entered the boundaries of our solar system and attracted the widespread attention of the scientific community. Specifically, this concerns two of the most well-known such objects, Oumuamua and 2I, Borisov. Oumuamua, discovered in October of the year 2017, shattered existing expectations and stereotypes because it did not exhibit typical cometary activity, despite following a hyperbolic orbit that clearly indicated its extraterrestrial origin. Unlike conventional comets, with their characteristic bright tails and activity, Oumuamua remained essentially inert, more resembling a falling asteroid or meteorite than a typical icy comet. Moreover, its behavior was even more enigmatic. It exhibited a small but measurable acceleration that could not be explained solely by gravitational forces acting on the object. This unusual acceleration sparked a storm of speculation, heated debates among scientists, and gave rise to theories about its possible artificial origin. If the object were a derelict spacecraft or somehow connected to remnants of extraterrestrial technological activity, then this acceleration could have a logical explanation. However, explaining such an effect for a natural object proved to be extremely difficult, which raised even more questions. In contrast, the second interstellar visitor, named 2I Borisov and discovered on August 29, presented a completely different scenario. This object behaved like a typical comet, showing a noticeable increase in brightness, the appearance of a tail, and characteristic expansion as it approached the Sun, which fully aligned with existing notions of comets. Spectroscopic studies revealed that its composition matches that of comets observed in our own solar system, indicating that the processes of comet formation are universal and occur independently of the specific conditions in which these bodies form, whether within our system or beyond. While Oumuamua represented an anomaly, entirely outside the usual characteristics, 2I Borisov was a vivid confirmation that natural comet formation processes can be similar across different star systems. As for the trio of asteroids known as the three Atlas, they occupy an intermediate position between these two extremes. The object exhibits clear signs of a cometary nature, a prominent cometary tail, rapid brightness increase, and a high content of carbon dioxide in its composition. However, its physical and chemical properties raise certain doubts. They do not fully match the characteristics typically associated with local or interstellar comets. Features such as unusual polarization properties and the relatively rapid expansion of the comet suggest a combination of factors that challenge the existing classification. Particularly important is the question of the nucleus size, as it directly influences the interpretation of other observed characteristics. Modern observations using space telescopes suggest that the radius of the object of interest is in the range of a few kilometers. This conclusion significantly differs from earlier assumptions, which proposed the existence of a huge, almost monstrous body with a diameter of 50 kilometers. Initially, such ideas arose from limited data and excessive hypotheses. However, current observations clearly indicate that we are dealing not with a giant but with a much smaller object. Knowing that the object is small plays a crucial role, as it imposes significant constraints on the amount of material available to form an extensive comet and its characteristic tail. A small nucleus, in essence, does not have enough mass to contain a substantial reserve of volatile substances capable of sustaining the high activity observed in the case of the three Atlas. Unless this activity is explained by extremely high process efficiency or the core composition differs radically from that of most known comets, such contradictions raise serious doubts about the natural origin of the object. In this case, it becomes logical to assume that if three atlases show behavior inconsistent with typical comet characteristics, then perhaps we are dealing with a completely different, artificially created structure. After all, Occam's razor suggests that the simplest explanation capable of accounting for all observed phenomena is most likely correct. Therefore, astronomers, before concluding on the possible artificial origin of the object, carefully investigate all possible natural mechanisms that could explain its unusual behavior. Among the many hypotheses, those proposing the presence of an unusual composition or structure inside the object, differing from the standard characteristics of solar system comets, occupy a special place. For example, a composition rich in volatile substances with chemical makeup significantly different from familiar comets could explain early activity onset and unusual chemical reactions. Surface texture and structure also play an important role. They can significantly influence the efficiency of gas and dust emission when heated by solar radiation. Rapid rotation creates centrifugal forces that can enhance the ejection of material from the nucleus and promote tail formation. Internal cracking or fragmentation may expose new areas rich in volatile components, leading to increased activity under solar heating. A key tool for investigating such features is polarimetry data, which provides especially powerful diagnostic information. When light reflects off dust particles forming the comet, the orientation of the light waves contains hidden information about the size, shape, and composition of these particles. By measuring the degree of polarization of the reflected light, scientists can determine the characteristics of the scattering material that remain hidden in simple brightness measurements. The 3 Atlas object exhibits unique polarization properties that do not match any previously studied object in the solar system, neither a comet, nor an asteroid, nor any other celestial body. Particularly striking are the extremely negative polarization values at small phase angles, reaching a minimum of about -7% at approximately 7 degrees. Such unusual measurements are unprecedented in research and cast serious doubt on the current understanding of light scattering processes by dust particles. These anomalous polarization properties may indicate the presence of unusual characteristics of field grains, which, in turn, challenge conventional models of light interaction with dust and space. During long interstellar journeys, a comet passing through interstellar space encounters unusual phenomena and exotic compositions. Scientists have discovered that as a result of such travels, rare and unique materials can form on its surface, materials not found in objects within our solar system nor even in artificial structures created by humans. These materials differ in their chemical and physical structures, often exhibiting optical properties that are unlike anything typically encountered in nature. In scientific commentary based on the opinions of leading researchers and published in academic blogs, preprint servers, and scientific journals, these unusual features are acknowledged, although most scientists remain cautious in their interpretation. The polarization properties observed in the data are genuine and raise serious questions, as they represent something entirely unusual and mysterious. However, to make claims about the existence of something supernatural or artificial, convincing and extraordinary evidence is required, evidence that is currently lacking. The hypothesis that the comet might be an artificial object faces several serious challenges. In particular, none of the numerous observatories conducting radio signal searches have detected any confirmation of radio waves emanating from this object. Despite intensive searches, the comet shows no signs of active control or trajectory correction through maneuvers, which would suggest interference by an intelligent civilization. Its path, although beyond the typical range for natural bodies, remains fully consistent with the laws of gravitational dynamics, and explaining it does not require invoking exotic propulsion systems or technologies. Moreover, if we assume that this comet is an artificial object, it would imply that the technological civilization that created it possesses capabilities far beyond current human understanding. Traveling from its home star system to our solar system, even at speeds comparable to the fastest spacecraft ever launched, would take thousands or perhaps tens of thousands of years. This means that only a highly advanced civilization capable of launching such long-distance interstellar missions would have the technology to do so, technology that radically surpasses our current knowledge and capabilities. Alternative hypotheses based on natural causes require expanding our understanding of the physical properties of comets and the chemistry of interstellar space. Perhaps these unusual properties are explained by unique chemical compounds or physical processes inherent to interstellar bodies, and do not necessarily imply the existence of advanced extraterrestrial technologies. Although the detection of such comets as the 3 Atlas certainly broadens our understanding of the capabilities of natural objects, it does not yet cross the threshold where assumptions about artificial elements begin. In the near future, as new data accumulates and observations continue, the scientific community will gradually be able to formulate the most probable hypothesis explaining the unusual characteristics of these objects. This process may take months or even years, as a systematic analysis of all collected data will be necessary to reach definitive conclusions. Ultimately, the weight of the evidence and its interpretation will determine whether the scientific community leans toward natural explanations or considers the hypothesis of possible extraterrestrial origin. If the hypothesis of artificial origin is confirmed, it would represent a true breakthrough, the first verified contact with a technological object originating from another star system. Such a discovery would radically change our understanding of humanity's place in the universe and open new horizons for science and technology. In this case, we could speak of the first encounter with something clearly created by intelligence and possessing technological capabilities previously unimaginable. But before making such revolutionary conclusions, it is essential to carefully consider the possibility that this object is not unique but merely part of a larger structure or phenomenon. And what if this comet is just one piece of a broader puzzle? Part 7. Hypothesis on the origin of the debris clouds. Sometimes the most unexpected and unusual explanations arise from events that initially seem catastrophic and destructive. Such situations can sometimes shed light on the origins of mysterious objects appearing in our sky. One possibility is the hypothesis that the so-called 3ALS, an unusual and enigmatic cluster of clouds composed of randomly scattered particles and debris, represents remnants of a long-past cosmic catastrophe. This catastrophe could have occurred thousands or even millions of years ago in a distant star system, making its investigation particularly fascinating and complex at the same time. The spread of this hypothesis expands the boundaries of our imagination, allowing us to suppose that even the largest destructions in space do not necessarily vanish without a trace. All of this remains within the framework of known physical laws, without requiring explanations involving supernatural forces or unverified theories. The debris clouds in question may have formed as a result of various mechanisms capable of ejecting material beyond their system at sufficient velocities to reach neighboring star systems. One such mechanism is the process of planet formation, which in the earliest stages of stellar system development is characterized by extreme chaos and intensity. During this period, massive bodies collide with each other, breaking apart into smaller fragments and ejecting a vast amount of debris into space. This era is considered one of the most tumultuous in the evolution of any star system, as collisions and fragmentation occur constantly, leading to the formation of new celestial bodies and their subsequent dispersal across interstellar space. Throughout the history of our solar system, such processes have been an integral part of its formation. For example, it is believed that the Moon formed after a collision between Earth and an object roughly the size of Mars, which resulted in a massive release of debris that eventually coalesced into a single satellite. Additionally, there is another significant mechanism: close encounters between two star systems, which occur at distances close enough for strong gravitational interactions. As a result of such encounters, gravitational forces can eject particles and objects from their original orbits, creating a stream of debris capable of traveling between different systems. Modern computer simulations show that these close encounters happen regularly throughout our galaxy's history. This creates a constant flux of interstellar wanderers, objects that travel without attachment to any particular system and can be found anywhere in interstellar space. Even more dramatic and large-scale are situations involving the destruction of entire planets or major satellites. Catastrophic events of this kind can scatter enormous masses of debris over incredible distances, whether caused by tidal forces during close approaches to another star or satellite, internal planetary processes, such as uncontrolled greenhouse effects, or even planetary-scale technological disasters. All these scenarios suggest that, as a result of such events, expanding shells of material are formed, moving at significant speeds through interstellar space. These shells are clouds containing numerous fragments flying toward the future. The composition of such clouds is of particular importance in the context of their origin, for example, being rich in carbon dioxide, which can serve as a potential key to understanding their formation conditions. The chemical makeup of these clouds indicates that they could have formed in extremely cold environments, where carbon dioxide in the form of ice remains stable for very long periods. These conditions most likely existed in the outer regions of another star system, where temperatures and pressures were so low that carbon dioxide ice could remain solid over geological timescales. In that case, the debris clouds could have formed precisely there, in the disk of the destroyed system, as a result of extensive destruction. The previously discussed anomalies in polarization may serve as crucial evidence of a field associated with the debris scattered throughout interstellar space. Considering the 3 discovered atlases, created from material that underwent different processing during formation or experienced unique conditions during its interstellar journey, it is quite logical to hypothesize that these dust particles possess optical properties not found in our immediate environment. These unusual textures and structural characteristics of the dust could be the result of extreme conditions, such as shock impacts during catastrophic ejections or the gradual alteration of the composition and properties of dust particles under the influence of interstellar radiation over millions of years. However, the presence of several objects temporarily gathering in our sky does not constitute absolute proof of their common origin. There may be a coincidental appearance, as if multiple unusual objects emerge simultaneously within our observable space. But this does not necessarily indicate that they are connected by a single source. Such an impression can arise due to observational bias and improvements in detection technologies, which allow us to identify faint and elusive objects. Today, our sensitivity and accuracy far surpass what we had 10 years ago, enabling us to notice phenomena that previously went unnoticed. That is why objects that once seemed invisible are now becoming apparent and attracting increased interest. Moreover, special conditions during solar maxima, such as the year 2025, can play a significant role in intensifying observations of comets and other small bodies. During periods of high solar activity, the interaction between the solar wind and the interstellar medium becomes more vigorous, causing comets to display brighter and more dramatic activity in their atmospheres. This, in turn, increases the likelihood of detecting objects on the edge of our detection capabilities, making them more noticeable and generating greater public and scientific interest than during solar minimum periods. If the hypothesis about the existence of a field associated with debris is indeed correct, and the 3 atlases represent only a small part of this broader field, then in the coming years we can expect the appearance of new interstellar objects passing through our system. Modern programs, such as the Legacy Survey of Space and Time conducted at the Vera Rubin Observatory, will significantly expand our ability to detect faint and fast-moving objects. This will allow us to better understand how diverse and numerous the population of interstellar visitors passing through our region of space is, often remaining unnoticed. The idea of a debris field becoming more and more plausible when considering how such material spreads over time. Imagine that debris resulting from a major cosmic catastrophe is similar to confetti scattered from a moving vehicle. Initially, these particles move together in a clustered group, but over thousands or millions of years, gravitational interactions with interstellar objects and stars gradually disperse them across an ever-expanding volume of space. From our vantage point, the observer's perspective on Earth, detecting individual fragments of such an ancient and large-scale event is very much like trying to identify separate parts of a fireworks explosion viewed from 1,000 miles away. The time after the initial explosion or catastrophe transforms these shards into scattered pieces, moving in different directions and existing at different times, which greatly complicates their recognition and correlation into a single picture. To determine their origin and understand that all these fragments stem from the same event, a thorough analysis of their composition, dynamics, and distribution is necessary. What compelling evidence might confirm the hypothesis of a field filled with debris? Primarily, common signatures in the composition and texture of several interstellar objects discovered during the research. If these properties, related to movement and trajectories that can be traced back to their common source, become even more convincing supporting arguments for this hypothesis. Modern computer models provide a powerful tool for testing such assumptions, allowing us to simulate how debris from various types of catastrophic events disperses in space and time. If the results of these simulations match current observations, that is, predict the distribution and composition of debris consistent with what we see in reality. Then such an explanation based on a cloud of interstellar fragments will gain even greater significance and credibility. The timescales required for the development of such scenarios truly go beyond human imagination. Imagine that the catastrophe that created this cloud occurred 10,000 years ago in a distant star system located 50 light-years away from us. This would mean that a comet or similar object was moving through interstellar space even before civilizations capable of agriculture arose. And the very tragedy that gave rise to this fragment could have occurred at a time when our ancestors were still hunters and gatherers, completely unaware that cosmic violence disperses shards that, over time, will reach their distant descendants. In a broader sense, and from the perspective of the hypothesis concerning the existence of a cloud of interstellar debris, it represents a kind of compromise between the idea of exotic natural phenomena and the hypothesis of artificial origin of these objects. This concept does not require violations of known physical laws, nor does it assume the presence of advanced extraterrestrial technologies or conspiracy theories about hidden government knowledge. It merely prompts us to consider that the galaxy may be far more brutal and chaotic than it appears at first glance, in contrast to the relatively calm and stable situation that has developed in our solar system. The implications of this hypothesis go beyond a simple explanation for the appearance of the triad. If interstellar clouds of debris are indeed widespread, they could serve as natural laboratories for studying the processes of planet formation in other stellar systems. Every shard, every fragment carries information about the conditions and materials that existed during the initial catastrophe, providing a unique opportunity to understand the evolution of stars and planets, which would otherwise be impossible to discover. This entire body of data has the potential to open new horizons in understanding the origins of the cosmos. However, it should be noted that the origin of debris from ancient catastrophes is only one hypothesis. It is also possible that the three Atesh and their satellites are not accidental remnants of cosmic accidents, but deliberately sent scouts from a civilization that considers our solar system as a potential territory for exploration. In the eighth part of this theory, the focus is on scouts. In the 1960s, mathematician and physicist Ronald Bracewell proposed an idea that has since become one of the key directions in the search for extraterrestrial intelligence. Instead of relying solely on transmitting radio signals across interstellar distances, he suggested that advanced civilizations could send autonomous probes, messengers, to neighboring star systems. These explorers, in his view, would be far more effective than radio waves for obtaining detailed information about distant worlds and their inhabitants. The logic of this approach appears quite convincing from an engineering standpoint. Radio signals weaken significantly over long distances, following the inverse square law, which makes communication between star systems increasingly difficult and unreliable on galactic scales. Nevertheless, if the possibility of sending interstellar probes is considered, such a probe would have a unique opportunity to penetrate the target system and conduct detailed investigations of the environment and objects there using specialized sensors and instruments. These technologies are generally not accessible for deployment across light-year distances because the scale and complexity of such systems require direct presence. This would resemble the concept proposed by mathematician John von Neumann, who was already known in the mid-20th century, describing the idea of self-replicating machines, devices capable of creating exact copies of themselves using locally available materials. Combined with the theory of probes, or the so-called Bracewell messenger, it can be hypothesized that such self-replicating devices could spread throughout the galaxy, forming a network of observation and reconnaissance. Each of these probes, upon reaching a star system, could begin producing new copies, leading over time to an expansion of their presence. Over millions of years, such a program could fill the entire galaxy with a network of devices capable of collecting and transmitting information about various worlds and conditions beyond our system. Applying these theories to a hypothetical interstellar visitor, such as a Type 3I Atlas object, raises questions about its possible role as a scout. Instead of openly demonstrating its artificial nature through obvious technological signatures, such an object could disguise itself as a natural comet, appearing and behaving like a typical celestial body. In this case, it could perform numerous observational tasks within our solar system without arousing suspicion among observers. This approach would be extremely effective from a stealth perspective. Natural comets possess unique characteristics that provide excellent camouflage for interstellar craft. Their orbits are predictable and well studied, allowing for planning their passages to maximize observation opportunities of multiple objects during a single pass through the inner solar system. For example, the trajectory of a Type 3I Atlas object could pass near Mars, enabling the study of its atmosphere and surface, then continue inward for more detailed observations of Earth and Venus. The timing of such a probe's arrival could have strategic importance. If it was designed to assess the technological development of civilizations, its appearance during a solar maximum, the peak of solar activity, would offer additional opportunities to observe our planet's reactions to space weather phenomena. Such a probe could monitor our satellite systems, power grids, communication infrastructure, and other critical objects, identifying vulnerabilities and collecting data that could be useful for future interactions or defense. Unusual brightness behavior of the object could serve not only as a natural effect related to gas emissions or chemical composition changes but also as a deliberate means of communication. For example, if the Object 3I Atlas were equipped with sensors and data transmission systems, the controlled changes in its visible brightness could serve as a communication channel or system test. A rapid increase in brightness, resembling a comet's expansion, could be the result of specially deployed sensor arrays or communication antennas disguised as natural cosmic phenomena. Using a chemical composition rich in carbon dioxide could be a deliberate design choice rather than a coincidence. Such gas would provide an efficient source of controllable gas emissions necessary for course correction and orientation of the spacecraft, while maintaining the appearance of a natural cometary body. Thus, a probe utilizing carbon dioxide as fuel and as a masking element could perform precise navigational maneuvers while remaining virtually undetectable. Its anti-tail geometry, the area opposite the tail, could serve a dual purpose: as a natural effect arising from observational and viewing conditions, and as a structural feature designed to enhance concealment. These architectural and structural solutions significantly improve the efficiency of solar panels, transforming them into powerful energy sources even in the harsh environment of space. If the examined probe is equipped with modern power systems, it could autonomously navigate through space using specialized algorithms and sensors to optimize solar energy collection. As a result, the artificial object could adjust its position to maximize solar energy absorption while creating visual effects that enhance its resemblance to a comet or other cosmic body. Such illusions could serve as a protective mechanism or a form of camouflage, especially important during reconnaissance missions in alien star systems. Particular attention is given to the extreme polarization characteristics of the radiation, which often represent the most mysterious and intriguing aspect of the hypothesis regarding the origin of such objects. Unlike natural dust particles, which in space never produce polarization signatures similar to those observed in the hypothetical object designated as 3ATLS, artificially manufactured materials, designed for specific optical or electronic functions, could indeed exhibit such unusual scattering properties. This opens interesting possibilities for the identification and analysis of similar objects, as modern engineered materials can demonstrate unique optical features that differ from natural samples. Next, let us consider the requirements for materials from which an interstellar probe could be constructed. Such a spacecraft must possess the ability to withstand numerous dangers associated with prolonged exposure to the interstellar medium. First and foremost, it must be protected from the effects of cosmic rays and space dust, which can cause serious damage to its systems. Additionally, the spacecraft is required to withstand extreme temperature ranges that occur during interstellar travel, as well as upon arrival in new regions of space where conditions can differ significantly from those within our solar system. To achieve this, modern developments utilize special composite materials or exotic coatings specifically designed for such purposes. These materials possess unique optical properties that are simply not found in nature, allowing for enhanced protection and functionality of the probe. The small size of the interstellar craft's core likely serves as another advantage supporting the hypothesis of its reconnaissance purpose. With its compact dimensions, such a probe can carry advanced instruments and communication equipment without the need for bulky structures. Modern miniaturization technologies have advanced to the point where powerful scientific tools can be housed in smaller bodies than traditional satellites. Furthermore, the development of civilization technologies capable of interstellar travel enables even greater miniaturization while maintaining or even increasing the device's functional capabilities. This means that within just a few kilometers, comparable to the characteristics of the hypothetical object, complex systems previously accessible only to large space platforms can now be concentrated. However, the idea of a reconnaissance device similar to this hypothetical object faces significant observational challenges. Despite extensive monitoring through radio telescopes located worldwide, signals that could indicate the existence of such an object have not been confirmed. Specifically, the probe shows no signs of active maneuvers, course changes, or other indications of control, which would suggest deliberate guidance. Its trajectory, although unusual and certainly attention-grabbing, remains within the laws of gravitational dynamics within the entire solar system and does not raise suspicions of artificial interference. The technologies required to carry out interstellar reconnaissance missions would be truly impressive. Such a probe would need to withstand prolonged periods of operation in the interstellar environment, rich in radiation and space dust, maintaining the functionality of complex systems for thousands of years. It would have to perform numerous tasks, from data collection to transmitting information back to Earth, despite vast distances and extreme conditions. In the scale of the universe, even a short period allocated for research and discovery seems negligible. Nevertheless, the coincidence of the mysterious probe's arrival at a time when humanity is in the early stages of developing its technology and knowledge seems incredibly convenient and even astonishing. Such a coincidence raises many questions and hypotheses, especially considering that the features of this object, 3 anomalous technological traces or signs, designated as 3 ATCs, and its timely appearance create a very convincing and logically coherent narrative structure. If humanity were developing interstellar reconnaissance missions, many of the observed characteristics of this probe would have quite specific and rational explanations from an engineering perspective. For example, it could be gathering data about our planet's atmosphere, studying its magnetic field or technological infrastructure, while remaining undetectable and simulating purely scientific observations of natural phenomena. Its trajectory toward Earth offers unique opportunities to study various worlds within our system, making the most of the enormous investments required for interstellar travel and reconnaissance. The most intriguing aspect of this situation is the hypothesis that if the 3 ATCs are indeed scouts belonging to an advanced civilization beyond our solar system, then it is most likely that they are not operating alone. It is quite possible that this cluster of unusual objects in our sky is the result of coordinated efforts by several reconnaissance devices sent from different points in space. Such devices could conduct simultaneous observations, covering different sectors and directions, which would allow for a more comprehensive and accurate understanding of our planet and its surroundings. However, this very possibility raises perhaps the most important and pressing question that preoccupies scientists and researchers. If civilizations exist in our galaxy that are sufficiently advanced to launch interstellar reconnaissance missions, why has humanity not yet discovered convincing and unambiguous evidence of their existence? Why do we not encounter confirmations of their presence and activities? The answer to this question may lie in one of the most well-known and mysterious scientific problems, the Fermi paradox. Named after the renowned physicist Enrico Fermi, this paradox arose in the mid-20th century. In 1950, during an informal lunch conversation at Los Alamos National Laboratory, he was asked a question that has since haunted scientists worldwide: where is everyone? This brief but profound question highlighted the deep and unresolved contradiction between the apparent likelihood of extraterrestrial civilizations existing and the complete lack of clear evidence of their presence. At the core of this question lies a serious mathematical model known as the Drake equation, developed in the 1960s by the renowned astronomer Frank Drake. This equation aims to estimate the number of civilizations capable of interstellar communication and interaction based on a variety of factors, such as the rate of star formation in the galaxy, the proportion of stars with planets, the number of habitable worlds in each planetary system, and the probability that life on these planets could develop intelligence and technology. Even with the most conservative estimates using the Drake equation, it is assumed that our galaxy should contain thousands or even millions of technologically advanced civilizations. Considering that the Milky Way has approximately 400 billion stars and that the galaxy's age exceeds billions of years, providing ample time for the development of intelligent life, the absence of obvious evidence of their existence seems statistically very unlikely. This contradiction forms the essence of the Fermi paradox. Within this paradox, numerous hypotheses and theories arise to explain why we do not encounter extraterrestrial visitors or their traces, despite the presumed widespread distribution of life throughout the galaxy. The detection of interstellar objects, such as these fragments found in space, provides valuable information that helps us better understand the prevalence and characteristics of planetary systems scattered across the galaxy. Each interstellar cometary object carries unique chemical signatures that can reveal details about the elements and compounds from which the star systems they originated are composed. By analyzing the chemical makeup of such objects, scientists can gain insights into the processes of planet formation and how frequently conditions suitable for life develop around other stars. In particular, a rich carbon dioxide chemical palette, characteristic of some of these objects, may indicate that such comets originated in more distant regions of the system, where temperatures are low enough for carbon dioxide ice to remain stable over geological timescales. These cold regions, located in the far parts of debris disks surrounding stars, could serve as sources of raw materials for future biological processes. As a result, such conditions are found in various systems, suggesting a widespread distribution of potential building blocks for life throughout the galaxy. If we assume that intelligent civilizations indeed exist elsewhere in the cosmos, it is quite plausible that they use such interstellar objects as tools for reconnaissance or observation. In this context, such a strategy seems particularly effective, as utilizing natural comets and asteroids as cover allows them to conceal their activities. This tactic is especially justified during periods of increased cometary activity, such as when multiple objects are passing through our solar system simultaneously. At such moments, it is difficult to distinguish an artificial object from a natural one, making them ideal for covert reconnaissance purposes. The current congregation of comets and asteroids observed this fall creates precisely such conditions, allowing potential extraterrestrial observers to remain unnoticed. From this perspective, the paradox associated with the so-called comet farm may have a very simple explanation. It is possible that extraterrestrial visitors are already here among us, and are highly advanced enough to avoid detection while conducting their observations. Instead of demonstrating their technology through bright and conspicuous displays, they prefer to leave their traces in silence, gathering information about our civilization as discreetly as possible. This approach helps them avoid potential conflicts or panic that could arise from obvious contact. According to this theory, such civilizations might be quite rare but still very real. They satisfy the Drake equation with low, yet non-zero, values for factors such as the probability of intelligent life emerging, technological development, or the longevity of technological civilizations. Even if only a small fraction of star systems are capable of giving rise to and supporting advanced spacefaring cultures, the vast size and age of our galaxy still allow for random interstellar reconnaissance missions. These missions can be carried out precisely because star systems sometimes happen to be connected with such means, even if they arose by chance. Regarding the unusual characteristics of 3A Tush, current natural explanations remain quite viable and perhaps more probable than assumptions about their artificial origin. For example, the volatile composition, rapid growth of the coma, and extreme polarization properties. All these features could result from natural processes occurring within an object with an exotic formation history or unusual internal structure. It is possible that such phenomena arise from interactions with the environment or internal geological activity, which is quite typical for certain types of celestial bodies. The detection of a large congregation of comets and asteroids in our sky region this fall may be more related to improved observation capabilities than to anything unusual or artificial. Modern technologies allow us to detect objects that previously remained outside our view, and dynamic processes within our solar system periodically lead to numerous objects crossing its inner regions. The principle of Occam's razor, widely used in scientific research and analysis, suggests that among all possible explanations for a phenomenon, the most likely one is the simplest, requiring the fewest assumptions. In other words, the fewer new hypotheses and complex assumptions needed to explain observed facts, the higher the probability that this explanation is true. In the context of natural phenomena, this principle indicates that most mysterious or unusual natural events can be explained by extending existing physical laws without the need to introduce complex or exotic hypotheses. For example, complex astronomical or geophysical phenomena are often resolved by expanding and refining known theories rather than positing new, unknown mechanisms. In contrast, when it comes to possible artificial explanations, accepting them would require assuming the existence of advanced technologies created by extraterrestrial civilizations, which is inherently a much more complex hypothesis. An important point is that such hypotheses demand the presence of technology that surpasses our current knowledge and capabilities, making them seem less probable and less simple than explanations based on known physical laws. Nevertheless, the possibility of such technologies or scenarios cannot be entirely ruled out. For instance, if we assume that interstellar reconnaissance probes truly exist and have been sent to observe other civilizations or planetary systems, their features, autonomy requirements, and stealth capabilities would be closely related to the characteristics we observe in so-called three-dimensional astronomical objects, or 3D ATOs, conditional objects that evoke our interest and suspicion. For long-term missions involving probes that remain in interstellar space for hundreds or even thousands of years, reliable, easy-to-operate systems capable of maintaining functionality over very long periods are crucial. Such systems must be resilient to harsh conditions, operate without constant maintenance, and have minimal complexity. Additionally, requirements for stealth and concealment of these devices imply the development of designs and technologies that allow them to imitate natural phenomena, such as meteoroids, cosmic dust, or celestial objects, helping to avoid detection by potential observers. The question of time becomes particularly relevant when considering the hypothesis of cosmic reconnaissance, as it seems strange why, within our brief historical window, just a few decades, possible contacts or observations of alien technologies are occurring. Our radio signals and radar transmissions, which began less than a century ago, have for the first time in human history reached a level where they could be noticed by extraterrestrials with advanced technology. At the same time, our space infrastructure, consisting of satellites, orbital stations, and other objects, has existed for just over 50 years. This remarkable coincidence, these potential contacts occurring precisely within this narrow timeframe, raises numerous questions about the randomness of such synchronicity. One possible hypothesis is that the appearance of observations and contacts is not related to some unique event or reaction to our technological achievements, but is instead a result of reconnaissance missions being a routine part of the activities of advanced civilizations. In other words, such missions could be carried out regularly, automatically, without connection to specific technological breakthroughs or crises. If we assume that advanced civilizations regularly survey neighboring star systems, paying little attention to the presence or absence of obvious technological signatures, then the arrival and deployment of probes would follow statistical and probabilistic laws rather than being directly tied to the development of particular civilizations. In this case, encounters with alien craft are not the result of an urgent mission but are a natural consequence influenced by numerous factors stemming from the depths of cosmic statistics. Alternatively, another hypothesis suggests that our own technological signatures might be detectable by others, implying that these observations could be part of a broader pattern of galactic activity. Looking at this situation from a different perspective, one could say that 3 astronomical atlases serve as our first tangible glimpse into what might be called the manifestation of a galactic civilization in action. Regardless of whether we are currently witnessing natural phenomena or encountering something more unusual and mysterious, the implications of such observations are impressive in their scale. Either the universe proves to be much more brutal, chaotic, and unpredictable than we assume based on the stability of our solar system, or we are observing evidence of a form of intelligence operating on scales beyond human comprehension and perception. This part of the research, known as the 10th, discusses the possibility of an alien invasion or extraordinary cosmic coincidences. Gradually, as the 3 atlases approach the inner boundaries of the solar system, the scientific community finds itself drawn into discussions that, just a few years ago, would have seemed absurd and incredible. However, despite the evidence still being far from conclusive, its accumulation has reached such a level that many respected experts are beginning to discuss hypotheses that go far beyond ordinary astronomical explanations. On one hand, astronomers with many years of experience studying comets and asteroids, and interpreting them based on classical notions of natural processes, participate in these debates. They point out that the unusual increase in the brightness of an object could be caused by interactions with exotic volatile compounds that respond to solar heat through complex mechanisms beyond our current models. Additionally, the geometry of the anti-tail, its shape, and direction reflect the influence of the viewing angle, as well as the complex distribution of dust surrounding the object, which explains many visual anomalies. Finally, the extreme polarization characteristics of the light indicate properties of field grains that differ from those observed in the solar system but still remain within the realm of natural processes. These scientists emphasize one important principle: any unusual claims require corresponding extraordinary evidence to be considered valid. And although the 3-tailed object exhibits signs of unusual properties, none of its characteristics can definitively rule out a natural origin. Perhaps the chemical composition, rich in carbon dioxide, the rapid growth of the comet, or its anomalous polarization, all of these can be explained by the possibility that the object originates from another star system, where the conditions for formation and subsequent processing of materials differed significantly from those in our local environment. On the other hand, the growing stream of opinions and voices within the scientific community underscores that the accumulating anomalies could indicate something greater than mere coincidence. The model suggesting the arrival of these objects during the fall of the next year, the 32nd year of the 20th century, with numerous bright comets and a wave of approaching asteroids, creates an impression of coordinated and possibly purposeful appearance. Such an impression is difficult to explain as mere coincidence, especially when the geometry of the anti-tail, green fluorescence, and rapid expansion of the objects combine into a single overall picture that almost seems deliberately designed to attract observers' attention. In this context, conspiracy theories and hypotheses about external organization of the processes emerge. Why, then, did so many unusual objects appear precisely within a narrow time interval? If their appearance had been uncoordinated and random, such a coincidence would be unlikely. The asteroid activity recorded in mid-September, combined with unusual comet manifestations and its striking visual features, creates a logical and natural narrative structure that suggests the presence of an external organization or even interference. Thus, it appears as though something larger and more complex is controlling these events, and their sequence and characteristics seem to be part of a unified plan or scenario. It is particularly important to emphasize that the 3 atmospheric telescope systems, designated as the 3 ATCs, pose no immediate threat to our planet. Regardless of the specific nature attributed to these objects, their potential impact on Earth is considered minimal or non-existent. In the near future, specifically on December 29, the comet will make its closest approach to our planet. At that moment, it will pass at a distance of approximately 1 astronomical unit, which is roughly 170 million kilometers. This distance significantly exceeds the space between Earth and the Sun, which is 1 astronomical unit, making any scenarios involving a direct collision or impact of this object with our planet entirely impossible and unrealistic. The comet's journey through the inner regions of the solar system will involve passing by several other planets. In particular, during its movement, it will approach Mars, Venus, and Jupiter, but these close encounters, from an astronomical perspective, will still occur at distances measured in millions of kilometers. Even if we assume that the three-atmosphere comet or a similar object is somehow artificially controlled or manipulated, it would not pose any threat to Earth or other planets in the solar system. Current knowledge and models do not suggest the existence of a mechanism that could allow such an object to harm our planet, even if its movement is carefully tracked and adjusted. The emotional and mystical allure of such phenomena, especially when involving the three Atlas objects with their unusual green glow, the geometry of the anti-tail, and rapidly increasing brightness, easily evokes associations with science fiction scenarios. The perception of such phenomena is often linked to extraterrestrial technologies or even supernatural forces, influenced by cultural background and our historical experience. In an era of popular culture and science fiction, we are accustomed to believing that any unusual astronomical events are necessarily connected to alien visitors or highly advanced technologies. Our societal consciousness, shaped by popular narratives, has laid the groundwork for dramatic interpretations of these phenomena. We expect that contact with extraterrestrials will inevitably be accompanied by loud proclamations, demonstrations of technology, or obvious signals that leave little doubt about their artificial origin. However, reality may prove to be much more complex and subtle. It is possible that such phenomena are merely part of reconnaissance missions or covert operations designed specifically not to provoke defensive responses from primitive civilizations, including our own. From this perspective, current discussions and speculations about extraterrestrial objects and their potential threats could very well be the tactics employed by advanced intelligence agencies. In this case, the purpose of such debates is to stimulate scientific interest and public discussion, rather than to provide immediate proof of extraterrestrial visitors. This approach allows for maintaining uncertainty, avoiding panic and societal chaos that could arise from irrefutable evidence of alien visits. The question of timing remains crucial for both sides, supporters of natural explanations and advocates of exotic theories. The latter argue that modern detection capabilities and increased public interest in cosmic phenomena create the illusion of heightened significance even for ordinary events. They believe that, thanks to advances in observational technology, we are now better at noticing and recording unusual objects, which sometimes leads to the perception that these objects are more important and significant than they actually are. That is why some argue that we have simply become better at identifying the unusual compared to previous decades. At the same time, proponents of more exotic interpretations are convinced that the accumulation of observed events exceeds the bounds of mere coincidence. They emphasize that the rarity of interstellar visitors and the relatively short history of systematic observations suggest that the coincidence of numerous unusual and mysterious phenomena occurring over a relatively brief period during what is called the early technological age of humanity requires a deeper explanation than simple coincidence or randomness. These events evoke the feeling that there is more behind their appearance than science or natural processes can explain, prompting the search for explanations beyond conventional understanding. Within the professional astronomical community, especially among scientists involved in data preparation and analysis for large-scale projects like the 3I Atlas, a stance of public neutrality is typically maintained. They prefer to avoid speculation and public assumptions about the nature of observed phenomena to preserve trust in scientific methodology. However, within scientific circles, it is often acknowledged that the characteristics of the discovered object significantly surpass all known natural samples previously studied by humans. This is especially true regarding data about its polarization, which does not match any known natural objects or phenomena, forcing scientists to either expand existing theoretical models or consider more exotic hypotheses related to possible artificial origins or other unusual mechanisms. The reactions of leading scientific institutions and observatories to these discoveries have been extremely cautious. Major observational stations, such as national and international astronomical centers, as well as space agencies, have focused on studying the technical aspects of the detected object. They have avoided speculative discussions about its nature and potential implications, limiting themselves to technical comments and preliminary conclusions. This conservative approach is driven both by strict scientific methodology, which requires data confirmation and avoids unfounded interpretations, and by practical considerations. Society fears the reaction to a possible discovery that could be perceived as a threat or shock. Nevertheless, the absence of new high-resolution images obtained from the largest space telescopes creates an informational vacuum, which naturally amplifies conspiracy theories and speculations about hidden information. In September of this year, observations did not add high-quality images to the database, raising certain suspicions. Explanations for this lack of data, related to technical limitations or scheduling conflicts, seem quite logical and justified. However, the period during which no new detailed images appears particularly convenient for those inclined to interpret the situation as more than just a technical obstacle. In this context, an important question arises. Are governments or scientific organizations hiding information about the object that has stunned them, especially if it truly represents something more than a natural phenomenon? If we assume that the object, known as the 13th object from Atlas, is indeed not just an unusual natural phenomenon but something more mysterious and possibly of artificial origin, then revealing this information could have extremely serious consequences for all humanity. No matter how difficult it is to imagine how governments and scientific institutions could handle confirming contact or reconnaissance by extraterrestrials, the social and economic reactions in the event of such a discovery could be catastrophic. The impact on religious beliefs, potential trust crises, crashes of financial markets, and the breakdown of international relations, these could all become a reality. For this reason, careful and gradual disclosure of information, accompanied by scientific debates and expert discussions, seems to be the most responsible approach. This method allows society to prepare for potential discoveries, adapt to new realities, and avoid panic or unfounded fears. The process creates space for the gradual acceptance of new knowledge that just a few months ago seemed unreachable or fantastical. As the so-called perigee, a critical point at the end of October when the chances of obtaining definitive and most convincing data are highest, approaches, each new observed aspect of the object becomes immensely significant. It could be decisive in determining its nature, either confirming or challenging existing hypotheses. Although the true nature of the object codenamed 3 Atlas remains unclear to the end, among scientists and researchers monitoring its development and features, a very troubling and simultaneously alarming question has begun to emerge. This question primarily concerns the lack of detailed, high-quality images, since such frames should have been captured by the most powerful and modern space telescopes. Surprisingly, the emergence of this question is linked to the absence in public sources, scientific databases, and informational resources of what would be obvious and expected, clear, detailed images of this mysterious object that would help better understand its structure and properties. This is especially relevant given that it concerns Part 11, a critically important phase of observation and research, when any missing information becomes particularly significant and raises numerous questions. The logical question arises: where are these images? Analyzing the observation records of the 3 Atlas, one can notice a noticeable and quite curious gap in the data, which raises serious doubts and uncomfortable questions among both professional astronomers and conspiracy theorists. While scientists continue to publish impressive photographs of the comet's green coma and the astonishing geometry of its tail, taken by amateurs and observers worldwide, major space observatories designed to gather data at the highest level remain silent or provide very limited information. This is especially evident during the decisive September period, when, logically, the most detailed and accurate images should have appeared to confirm or refute hypotheses about the nature of this object. For example, the Hubble Space Telescope, one of the most renowned and powerful instruments of modern times, captured detailed images of 3 Atlas on July 21. These images clearly show a compact core surrounded by a bright, dust-rich cocoon, resembling a protective shell. These photographs allowed scientists to establish important size constraints for the object and set basic parameters for its unusual characteristics, marking a significant step toward understanding this mysterious formation. However, despite more than 2 months having passed, that is, as of September 22, no new images from the Hubble Space Telescope have been published. Meanwhile, the comet continued to brighten, becoming increasingly noticeable and, in some cases, even dramatic in appearance. This created the impression that there was some secret being deliberately kept from the public. It is also worth noting that the James Webb Space Telescope, launched quite recently and equipped with unique spectroscopic capabilities, conducted observations on August 6, obtaining valuable information about the chemical composition of this object. Its spectroscopic studies revealed that the comet contains a substance rich in carbon dioxide, indicating unusual properties of its chemical makeup and possibly some unique processes occurring within. These pioneering studies quickly made their way into news outlets and sparked widespread public and scientific interest because they confirmed that the 3 Atlas is different from all previously studied comets, likely possessing its own, unique character. However, despite the ongoing evolution of the object and the growing interest, not a single image taken by the James Webb Telescope in September has appeared in open databases or informational resources. This raises even more questions and suspicions, especially considering that new data should have been delivered to the scientific community and become part of the collective understanding. As for the Gemini South Observatory, which is also observing this object, it published a stunning high-resolution image on August 27. It attracted widespread attention with its clarity and detail, providing valuable insights into the complex structure of the comet's tail and its unusual features. However, despite its impressive precision, this image was obtained a month before the key September period, on August 27, and was only published on September 4. This means that even the most high-quality and informative photo that could offer clues was released well after the initial observations. Research groups engaged in astronomical observations typically work under conditions of exclusive access to the data they collect. Such access is granted for predetermined periods, allowing scientists to thoroughly analyze the information, prepare scientific publications, and draw conclusions before the results are made available to the general public. This system serves as an important safeguard for the resources and efforts invested in research, ensuring that investments in scientific work are justified and not wasted without proper verification. At the same time, it provides quality control over the data and the possibility of expert peer review, ultimately enhancing the level of scientific conclusions. Processing telescope data often involves certain delays between the time of observation and the publication of results. This is due to the need for conducting complex calibration, analysis, and verification procedures. In order for the raw data obtained from the telescope to be fully interpreted and used for scientific purposes, a significant amount of work is required, involving multi-stage calibration and careful validation of the acquired information. In the case of complex observations, such as studying bright cosmic objects or temporal variations, these procedures can take weeks or even months, as it is essential to ensure the accuracy and reliability of the data obtained. An additional factor complicating the work of large observatories is the high demand on their resources. Telescopes like the Hubble Space Telescope or the newest James Webb Space Telescope receive a vast number of observation requests. Their capabilities are limited, and therefore difficult decisions must be made about which scientific goals deserve priority use of the valuable observation time. As a result, competition for slots in the schedule of these powerful instruments becomes highly intense, and scientists are forced to compete for limited time to demonstrate the significance of their projects. Against this backdrop of constraints, resource competition becomes especially acute for projects like TRE Atlas, which struggles to secure observation time among many other important scientific endeavors. Despite this, it is well known that the usual causes of delays and queues are the need for preliminary data processing and approval of observation plans. However, despite these explanations, there is a sense that sometimes gaps in public data seem inconvenient for those inclined toward more suspicious interpretations of what is happening. When September arrives, this period particularly draws heightened attention to observations of an object known as 3I Atlas. During this time, there is a rapid increase in brightness, deviating from expected light curves, as well as a noticeable green glow that becomes increasingly apparent. If government agencies or international scientific organizations were to discover something truly unusual and worthy of special attention in these anomalies, September would be the time when they might impose restrictions on information dissemination, conducting covert research and secret analyses. The absence of data in public sources during this period could indicate not only technical delays but also deliberate suppression of information, raising suspicions within part of the scientific community. Meanwhile, astronomy enthusiasts around the world actively fill the resulting informational vacuum with their own observations. Clear, cloudless skies over regions such as Namibia, Chile, or Australia have provided them with a unique opportunity to capture stunning photographs showing changes in the appearance of the object throughout September. These images have obvious scientific value, as they allow tracking the brightness dynamics and structural features. However, they often lack spectroscopic detail and precise calibration data that professional observatories can provide. This contrast between numerous amateur images and the scarcity of official professional data creates an unusual informational landscape, where the level of reliability and detail varies significantly. Social media is literally flooded with vivid photographs of the green coma and complex tail structures of 3I Atlas, posted by experienced amateur astronomers using modern equipment. While these images enable observers worldwide to see the appearance of the object and share their experiences, scientific databases, traditionally sources of reliable information, remain limited. Detailed chemical studies and analyses based on precise astrometric and calibrated photometric data continue to be essential tools for a deep understanding of the nature and unique characteristics of the celestial object known as 3I Atlas. Thanks to such research, scientists can identify nuances in its composition, determine behavioral features, and track changes occurring in its structure. However, it is noticeable that recently there has been a lack of fresh professional visualizations of this object, which becomes particularly significant when compared to the increasingly dramatic changes in the comet's external appearance. In a situation where the object's appearance exhibits more and more signs of unusuality, any new images could serve as valuable sources of information, helping to trace the dynamics of changes, understand the reasons behind unusual brightness variations, and identify possible causes for alterations in the shape and orientation of the anti-tail. Autumn, especially September, was expected to be a period of active observations, as this month was believed to mark the beginning of a noticeable increase in brightness, the development of intensified green glow, and possibly changes in the geometry of the anti-tail, which had been recorded in previous observations. These signs would indicate serious processes within the comet, its response to solar radiation, or potential changes in the composition of its nucleus. However, instead of the expected data available to the scientific community, we are faced with a significant gap. At the very moment when the most important and interesting events were occurring, information simply disappeared from public access. It is unclear why professional images or reports were absent at that time, especially since the comet showed signs of activation during this period. This gap in observations raises suspicion that either such data was not collected at all or that access to it was more strictly controlled than usual, ruling out accidental leaks or unplanned publications. Many experts note that the upcoming conjunction with the Sun is a natural and expected event that should have limited observation opportunities in October. Solar influence and increased solar activity create conditions in which observing the comet becomes extremely difficult or impossible altogether. However, this explanation does not clarify why, in September, when conditions were still favorable, there were no public or professional data available. For most of September, the comet remained clearly visible and accessible for observation, as the solar declination was moderate enough to ensure the safety of telescope operations. This allowed for detailed studies, tracking changes, and obtaining important information about its structure and behavior. The next significant point is the upcoming flyby of Mars, scheduled for October 3rd. This event represents the last optimal window for acquiring high-resolution images and data before the solar conjunction makes ground-based observations impossible or very challenging. During this period, several spacecraft already orbiting Mars plan to utilize their capabilities to study the comet at close range. This opens a unique opportunity to obtain detailed images of the nucleus and internal structure, which will help understand the composition of the three ATL components, how they form, and what processes occur within them. If successful, these observations could significantly enhance our knowledge of such objects and their interactions within the solar system. After the solar conjunction period concludes at the end of October and early November, the comet will reappear in the pre-dawn sky, becoming visible to ground observers. This reappearance is a rare chance for astronomers to conduct additional, more detailed studies, and to determine how its characteristics have changed during its close approach to the Sun. During this time, scientists will be able to observe potential transformations in the comet's structure, brightness, and emissions, which will help us understand how the comet reacts to extreme conditions near a star. However, the question remains, will observations after the conjunction fill the existing gaps in knowledge, or were the most critical data already collected in September, when access to professional observations was mysteriously cut off? This question is of particular interest in scientific circles, as it directly concerns understanding the true nature and composition of the three ATL components. The scientific community is eager and deeply invested in uncovering the truth. Yet, a mere gap in observations is only one element of a more complex and multifaceted picture, which leads some scientists and researchers to doubt that the coincidence of the brightest manifestations of the third Atlantic comet is merely coincidental. This aspect becomes especially important in the context of the entire observation system and astronomical events, as it indicates possible hidden causes or circumstances affecting the visibility of the object. The second part of the discussion is dedicated to what is commonly called the superior conjunction, the period when the comet is positioned behind the Sun from Earth's perspective, as if at a convenient dead point, unobstructed ly hiding it from observers' view. On October 25, a whole cosmic choreography unfolds, creating conditions that conspiracy theorists might call the perfect scenario for hiding information, while astronomers perceive it as an undesirable but predictable challenge for observations. This superior conjunction is the period when the orbital path of the object brings it to the opposite side of the Sun, rendering it practically invisible to observers on Earth. At this moment, when the comet is behind the solar disk, the Sun's brightness reaches such levels that directly looking at it or attempting to observe the object from the planet's surface becomes impossible. As a result, a so-called dead zone or blind spot arises, a temporary area where observers are unable to see the comet. It is precisely during this period, when the comet passes behind the Sun, that it reaches its most active phase, revealing all its mysteries but remaining invisible to terrestrial instruments. This cycle, governed by the laws of celestial mechanics, makes such moments inevitable. In particular, October 21st is the day when a new moon occurs, and simultaneously when the comet reaches its minimum solar elongation, that is, its closest position to the Sun in the sky. At this moment, the comet disappears from sight almost completely, as its light is overwhelmed by the dazzling brightness of the Sun. Consequently, even the most sensitive ground-based telescopes cannot detect it, and observations from space observatories become dangerous and impossible without special precautions. Operational groups conducting observations of such objects regularly suspend their work when the comet approaches low solar elongation angles, usually between 15 and 30 degrees from the Sun's position. These measures are not arbitrary or bureaucratic restrictions but are necessary to protect expensive equipment, often worth billions of dollars, from damage and overheating caused by scattered sunlight and thermal fluxes. These limitations are critical safety measures designed to ensure the preservation of highly sophisticated instruments that must operate under the most challenging conditions. The signal-to-noise ratio sharply deteriorates as the object approaches the superior conjunction point. Even if, in theory, instruments could safely point directly at the Sun, the brightness of its background and the faint signals from the comet would make observation practically impossible. This is similar to trying to photograph a candle flame while staring directly at a spotlight. The bright light source interferes with perceiving and capturing faint reflections. From the perspective of conspiracy theorists, all of this appears almost too convenient, as if it were a deliberately crafted scenario to hide information. If any government agency or international scientific organization had intentionally tried to silence or conceal the appearance of the Tri-Atlas at the most critical moment, it would be hard to come up with a more effective cover-up than the upper conjunction. At this point, the comet disappears from the public eye just when its unusual properties and characteristics should be most evident and intriguing. And it is precisely during this time, when the comet is hidden behind the solar disk, that it becomes unreachable by observational instruments and remains in the shadows, raising further suspicions among those inclined to see more than just coincidence in this. The period during which the comet approaches perihelion, the very moment when it is at its closest distance to the Sun, is usually marked by especially bright and dramatic activity. It is during this time that the comet demonstrates its most impressive displays, a brightly illuminated comet with a developing coma and a noticeable tail, stretching behind it like a glowing streak across space. However, it should be noted that this activity often coincides with what is called a conjunction eclipse, when the comet lies along the line connecting it to the Sun and Earth, significantly complicating its observation from our planet's surface. Tri-Atlas, one of the brightest and most noticeable comets of this period, will reach its closest approach to the Sun on October 29. On this day, the comet will achieve maximum density of its coma, the gas dust cloud surrounding the nucleus, and will become especially bright in the sky. At the same time, its tail will be most visible and extended, creating a spectacular sight. Despite the comet being at its most active during this time, observing it from Earth will be difficult because it will remain hidden behind the solar atmosphere, in a state of conjunction with the Sun. As the comet emerges from the conjunction with the Sun at the end of November, its peak activity will essentially conclude. However, even during this challenging observational period, a complete informational vacuum does not occur. Thanks to numerous spacecraft positioned at various points in the solar system, it remains possible to observe the comet from different angles and viewpoints, which are not limited by Earth's position and orbital orientation. These spacecraft provide valuable data about the comet even when it is inaccessible to ground-based observation. One such instrument is the Solar and Heliospheric Observatory, known as SOHO, which regularly scans the area around the solar disk and is capable of capturing events occurring near the Sun, including a comet passing through conjunction. This equipment helps record important details and changes happening in the coma and tail of the comet, even during periods when observations from Earth are impossible. Next in line are the systems that form part of the Stereoscopic Solar Activity Observation Observatory, called STEREO. It consists of two spacecraft positioned on either side of Earth, one ahead of its orbit and the other behind. These spacecraft work together to create stereoscopic images, allowing scientists to perceive the structure and dynamics of solar activity, as well as the inner heliosphere, in 3 dimensions. Thanks to their placement, they can conduct observations from angles free of solar interference, which is especially important during conjunction periods when direct observation is challenging. The European Space Agency also has a mission called Solar Orbit, which, orbiting on an elliptical trajectory, places its spacecraft far beyond the ecliptic plane. This positioning provides unique opportunities for observing the Sun and its environment, enabling the detection of Comet 3 Atlas even during times when Earth is in unfavorable conditions for direct observation. With these vantage points and high-resolution data obtained from above, specialists will be able to monitor the comet's development even during its conjunction with the Sun. Additionally, several spacecraft orbiting Mars are planned to utilize their capabilities to observe the comet during its closest approach to the Red Planet, scheduled for September 30th. Among them are high-resolution systems such as the High-Resolution Imaging Science Experiment, HiRISE, mounted on the Mars Reconnaissance Orbiter, as well as the Color and Stereo Surface Imaging System, CASIS, attached to the European ExoMars Trace Gas Orbiter. The Mars Express spacecraft also plays an important role, equipped with its own capabilities for high-precision observation of celestial objects, including comets. These instruments operate during the period when the comet is in conjunction with the Sun, coinciding with one of the most active phases of the solar cycle, specifically approaching the solar maximum, which occurs within the 11-year solar cycle. During this special period, solar activity significantly increases, manifesting as powerful coronal mass ejections, intensified solar wind, and numerous solar storms. These phenomena not only create bright and impressive interactions with various celestial objects but can also significantly influence near-Earth space. This is especially evident in interactions with comet tails, as strong magnetic and electromagnetic disturbances can completely sever a comet's ion tail or cause sudden and noticeable fluctuations in its brightness. Such changes are sometimes so bright and abrupt that they can be easily observed even by amateur astronomers using amateur observatories or simply binoculars. These natural solar-comet interactions can, in certain cases, mask or even mimic artificial phenomena, adding complexity to the interpretation of observations. As a result, there is some uncertainty regarding the true nature of the object known as 3I Atlas, particularly during the critical period of its conjunction with the Sun. If the comet were equipped with special systems created by humans, for example, remote-controlled engines or other technological means, the solar maximum could serve as a natural shield against sudden electromagnetic pulses or maneuvers caused by external influences. Under such conditions, it might have been possible to prevent undesirable changes in its trajectory or appearance. However, for scientific and practical analysis, it is crucial to restore its visibility in the sky after the conjunction period, as this will provide answers about its nature and origin. According to the latest forecasts, the comet is expected to exit the conjunction zone at the end of November, and at that time, it will become visible again in the pre-dawn light, allowing observers in both hemispheres to record its appearance. During this reappearance, the comet's brightness and external appearance will provide valuable information about how it has evolved and changed during its hidden stay in the shadow of the solar conjunction. If, after its reappearance, it appears unusual, with altered brightness, modified tail structure, or the emergence of other anomalies not characteristic of natural comet development, this will strengthen hypotheses about its artificial origin and the possible existence of certain technologies or interventions. Conversely, if the comet, after emerging from the conjunction, exhibits typical features of ordinary comets, predictable brightness decrease, standard tail structure, and no anomalous characteristics, this will significantly reinforce the natural interpretation of its appearance, indicating a natural origin and evolution. The time when the comet approaches Earth, December 20th, although at a distance of 8 astronomical units, will still create optimal conditions for observation. This period provides several weeks after the conjunction to allow the comet to rest from the solar glare and become accessible again to large ground-based and space telescopes capable of capturing the finest details of its structure and behavior. Already, astronomical societies and amateurs from around the world are preparing for this observational event. Networks of radio enthusiasts are being organized, information is being exchanged, and control protocols are being established to create the most complete and accurate image of this unique object. After emerging from the Sun's shelter, the comet will become a focus of close attention from both professional and amateur research groups. These joint efforts will ensure backup observations, helping to compensate for potential limitations or delays in the operation of scientific observatories due to technical or operational issues. The conjunction period with the Sun is not only about observation but also a deeper natural experiment, during which the capabilities for acquiring and transmitting information about cosmic objects and their interactions with solar activity are tested. It serves as a kind of testing ground where methods of control and monitoring are evaluated. Modern spacecraft equipped with specially designed sensors and instruments can conduct detailed and comprehensive studies of cosmic objects over specific intervals, even when they are in a shutdown or passive observation mode. These studies are usually kept classified and inaccessible to the general public until a political decision is made to disclose the information obtained. Such an approach to data management and secrecy is not unique in the modern world. It is typical for military and intelligence agencies, where confidential observations and intelligence data are often kept secret for many years, sometimes decades, to ensure national security and maintain advantages in intelligence and technology. The transition from a primary scientific discovery to a matter of national or state security can happen very quickly, especially if the discovered object or its characteristics draw heightened attention from the government or security agencies. In such cases, a situation that initially seemed to be a scientific or astronomical issue can turn into a problem requiring intervention by state authorities and measures to ensure security. At the same time, from a more optimistic perspective, phenomena of astronomical objects, such as unusual features of interstellar bodies, may simply result from unfavorable observational conditions or temporary circumstances that deprive the public of the opportunity to witness some of the most significant astronomical events in modern human history. The appearance of a comet on the horizon, scheduled for the end of November, has the potential to become a real breakthrough in the field of astronomy and interstellar research. This event could usher in a new era in understanding the nature of so-called interstellar visitors, as well as help better comprehend the characteristics and origins of objects emerging from other star systems. Within this phenomenon, the so-called superenvironment surrounding the object, designated as 3ALS, creates ideal conditions for those inclined toward conspiracy theories and assumptions about hidden motives. At the same time, it also offers quite logical, scientifically grounded explanations capable of satisfying even the most skeptical scientists and researchers. The feeling that everything happening, including the peculiar behavior of this interstellar guest, seems deliberately chosen and designed to maximize uncertainty and stimulate public debate appears very evident. The timing of these events, along with gaps in observation and analysis, creates the impression that all of this is part of a carefully planned game. However, such features are not limited to this alone. They seem to be borrowed from classic science fiction scenarios, where technological and scientific discoveries are accompanied by global mysteries and dangers, sometimes seemingly beyond the comprehension of ordinary people. Sometimes the situation resembles a plot from a satirical film depicting a similar scene, ignoring or suppressing obvious threats until they reach a critical point, after which it becomes too late for effective response measures. A film created for the Netflix platform and released in 2020 tells a darkly comedic story in which authorities, media figures, and large corporations systematically hide or distort information about an approaching comet threatening to destroy all life on Earth. Although this film is intended as a satirical critique of climate change denial and political inertia, parallels with the real situation of the interstellar object 3IATL seem especially striking and unsettling for observers who see them as alarming signals. In the film, astronomers discover a massive comet on a trajectory foretelling a catastrophic collision with our planet. However, despite the obvious threat, they face strong resistance. Their attempts to inform the public are blocked by bureaucratic structures and distorted by mass media, which tend to give these events an entertainment or political tone. This entire situation resembles a game on the edge of secrecy and disclosure. The description presented in the film, state secrets and information management, echoes and highlights existing gaps in informational transparency, especially around the so-called 3I Atlas. This film pays particular attention to the fact that authorities and officials know much more about the properties and characteristics of the approaching celestial object than they are willing to disclose to the general public. During the escalation of events, they conduct highly classified assessments and studies, keeping the true situation behind the scenes, while pretending that everything is under control, that the situation is under full surveillance and management. However, there is a significant difference between the fictional scenario and reality, which helps to understand how strongly the world is influenced by information flows and how dangerous distrust in official sources can be. In the fictional work, Don't Look Up, the comet in the plot represents an immediate threat to Earth's existence, creating an atmosphere of panic and an urgent crisis. In contrast, the real object, 3I Atlas, was discovered over a year ago, and its trajectory has already been precisely calculated by scientists. Its approach to Earth is planned so that it will pass at a safe distance, about 18 astronomical units, which is roughly 18 times the distance from Earth to the Sun, and it will occur on December 29. Even the most daring and exotic theories about the nature of this celestial object do not suggest any immediate physical threat to our planet. Unlike the film's plot, where the comet was discovered only a few months before the predicted collision, causing mass panic and a sense of urgency, the real object has long been under close observation, and scientists are confident in its harmlessness. This important distinction highlights another aspect. In reality, the possibility of a collision or direct impact is as minimal as the absolute absence of any probability that the object will hit Earth. Nevertheless, the psychological reaction of the public, especially amid information isolation and limited transparency, largely mirrors what is depicted in the film. On social media and various internet platforms, there is a heated debate and competition between different theories, from simple and understandable explanations based on scientific data to more exotic and fantastical hypotheses suggesting that the object could be a reconnaissance satellite or even an interstellar visitor. This polarization of feelings and opinions between authoritative scientific sources and skeptics opposed to official information is one of the central elements satirized in the film, but in real life, it manifests very vividly. Media coverage and sensationalism, as shown in the movie, are also reflected in real news headlines concerning 3I Atlas. In mid-September, reports emerged about objects passing near Earth that attract the interest of scientists and the public, whether asteroids flying close to our planet or mysterious interstellar bodies. These news stories are often accompanied by sensational headlines that promise to reveal new secrets or suggest the possibility of contact with extraterrestrial civilizations, which attracts attention and increases audience engagement. At the same time, behind the external brightness and spectacle, there is often a lack of thorough scientific assessment and fact analysis, which can mislead society and lead to a distorted perception of the actual level of danger. The film, Don't Look Up, vividly illustrates how legitimate concerns of scientists and their well-founded assessments are distorted and manipulated in the course of political battles and economic interests. As a result, priority is often given to short-term gains and political advantages, while long-term consequences and real dangers remain in the background. A similar situation is characteristic of the real scenario with the 3I Atlas, where complex scientific issues are interpreted through the lens of various interests, from government secrets to pressure from the entertainment industry and media corporations, which seek to attract public attention and profit from sensationalism. Within the framework of modern cinematic storytelling, where the struggle to maintain scientific authority is at the forefront, two opposing approaches to interpreting ongoing events often clash. On one side are strict scientists who adhere to rigorous scientific methodology, aiming to convey real facts and objective data to society. On the other side are charismatic figures, often with a bright personal appeal, who prefer to present information in a more emotionally charged and dramatized manner, often eliciting greater interest and emotional responses from the audience. In this context, debates about the Tri-Atlas project turn into a kind of arena where these two worlds collide, one based on strict scientific principles requiring thorough verification and transparency, and the other more vivid, dramatic, and captivating for a broad audience, often appealing to feelings rather than facts. In this confrontation, similar contradictions often arise. On one hand, they create the need to uphold scientific integrity and critically evaluate information. On the other, they foster conditions for more dramatic narratives that can captivate and confuse society. However, it is important to remember that the satirical structure of such films should not serve as an excuse to ignore or minimize genuinely important issues related to transparency and information exchange within the context of the Tri-Atlas project. When creating a fictional story, directors and screenwriters often use hyperbole and irony to highlight real problems. For example, the difficulties faced by large institutions in managing long-term tasks that go beyond usual political or economic interests. In this sense, the film functions more as a metaphor, drawing our attention to issues that require honest and open discussion rather than mere entertainment. A particular concern in this context is the lack of high-quality images from major space telescopes. The absence of new, high-resolution photographs, especially during moments when conjunctions and visibility conditions allow for such captures, creates informational gaps that naturally lead to speculation and conjecture. Society begins to suspect that this informational silence is the result of deliberate data concealment, reinforced by the feeling that hidden forces are trying to control or suppress important information. Although such theories may seem fantastical, they resonate with the collective consciousness, especially when operational constraints and technical difficulties provide justifications for delays or the absence of data. This scenario resembles the management schemes depicted in the well-known film, Don't Look Up, where government and scientific institutions appear unable or unwilling to fully disclose the truth, ultimately undermining public trust in their actions. The image of societal fatalism and denial, vividly portrayed in the artistic interpretation, also aligns well with contemporary views on astronomical phenomena. Many people perceive reports of approaching asteroids, new comet discoveries, or other cosmic events as mundane or even entertaining, ignoring their scientific significance and potential importance. For most, these news stories become sources of entertainment rather than prompts to consider that behind every observation lie important scientific discoveries capable of expanding our understanding of the cosmos. As a result, critical warnings and scientific breakthroughs often go unnoticed, which could have serious consequences when dangerous threats arise. Ultimately, the film, Don't Look Up, demonstrates that humanity's true vulnerability lies not so much in external threats like asteroids or cosmic disasters, but in our inability to process complex information adequately and to collectively respond to challenges that go beyond familiar political and economic cycles. This picture emphasizes that internal weaknesses and distrust in institutions often represent the primary risk factors for humanity as a whole. The situation with the Tri-Atlas project similarly raises questions about how effectively our core message is being communicated. The main takeaway from this film is that successfully solving complex and unusual problems often requires the collaboration of diverse fields and honest, open interaction that goes beyond the traditional boundaries of government institutions, scientific organizations, and other structures. In today's world, where global issues such as climate change, pandemic response, or potential first contact with extraterrestrial intelligence arise, the stakes are so high that ordinary political games filled with manipulation, intrigue, and distrust can no longer serve as effective tools. In such cases, informal cooperation based on trust and open information exchange is necessary, cooperation capable of overcoming existing borders and barriers. The film emphasizes that in these situations, it is crucial to go beyond traditional politics and social dysfunctions because, faced with imminent danger or the possibility of discovering new horizons, humanity must unite to find the most effective solutions. It reminds us that principles like honest communication and collaborative effort can be the key to overcoming challenges that seem insurmountable when viewed solely through the lens of political and social games. Of particular interest in this context is the situation involving the comet designated as 3IATLS. This scenario raises important and sometimes even philosophical questions about how humanity should respond to ambiguous but potentially revolutionary discoveries that could fundamentally alter our understanding of the nature of life and intelligence. The characteristics of the comet, which differ from the familiar, do not initially pose an immediate threat of destruction or catastrophe. However, its unusual properties suggest that this celestial body could herald significant changes in our understanding of humanity's place in the universe, as well as what we consider to be life and intelligence. These changes could be as profound and transformative as if the comet's core contained substantially more material than current estimates suggest. Specifically, the upper limit of the comet's radius, estimated to range from approximately 2 to 8 kilometers, was determined using data from the Hubble Space Telescope combined with ground-based observatories indicating a diameter of several kilometers. These measurements are currently the most accurate and reliable constraints on the object's size. However, it is important to consider that such measurements are based on assumptions about the comet's surface reflectivity and geometric properties, which may not be applicable to objects with unusual compositions or internal structures that differ from standard models. If the comet's nucleus were significantly larger, it would contain proportionally more volatile substances. This, in turn, could explain the rapid expansion of the comet and the unusual evolution of its brightness observed throughout the period of its approach to Earth. In such a case, we would be dealing with a situation where the increase in the comet's size and brightness corresponds to a larger reservoir of volatile materials, causing intense sublimation and expansion. However, such scenarios contradict the most carefully conducted and calibrated observations, and confirming them would require a systematic error across several independent measurement methods. Similarly, if during the flyby past Mars an event related to the fragmentation of the comet occurred, it could lead to subtle changes in dust emission and brightness characteristics. Comets sometimes undergo splitting processes when tidal forces or thermal stresses exceed the strength of their loosely bound nuclei, causing them to break apart. Such events are usually accompanied by a significant increase in brightness, as newly exposed surfaces rich in volatiles begin to actively sublimate under solar heat, enhancing their glow. If such fragmentation occurred near Mars, these changes could be considered physically plausible, given the gravitational stresses and resulting structural deformations. As a result, external signs of such an event, such as changes in the brightness curve, should have been recorded in the data. The accuracy of the obtained orbital solutions is explained by numerous measurements conducted over many months, gathering detailed data on the object's position and motion. Thanks to this extensive amount of information collected over a long period, it was possible to create highly precise trajectory models that are virtually impossible to falsify or manipulate. Any significant changes in the motion or position of this object would have required forces exceeding in nature and scale those generated by the gravitational attraction of known bodies in the solar system. In other words, to substantially deviate the trajectory, forces much greater than the gravitational influences of planets and other large bodies would be necessary, making any attempts to artificially alter the course extremely unlikely and practically impossible. Although outgassing from comet nuclei can cause small accelerations, such effects are minor and follow patterns related to solar heating and the comet's rotation periods. These non-gravitational forces typically manifest as predictable changes that are easy to model and account for in orbit calculations. In order for artificial moving systems to significantly deviate their trajectory, they would need to operate under very strict conditions, which would not only complicate their functioning but also increase the likelihood of detection by modern monitoring tools. Let's consider a hypothetical scenario where 3 ATS, automatic transport systems or vehicles, send out small reconnaissance probes or microsatellites disguised as natural meteoroids. Such an approach would require technologies capable of deploying and protecting payloads that could successfully enter Earth's atmosphere and operate on its surface while remaining undetectable to detection systems. Additionally, reliable communication with the main apparatus would be necessary, complicating the logistics of such operations. Precise time synchronization, miniaturization of equipment, and its resilience to extreme atmospheric entry conditions would all pose significant challenges for engineers and scientists. If, however, these artificial objects were launched from the 3 ATS, their trajectories, governed by orbital mechanics and deployment conditions, would be predictable. They would follow established models based on physical laws and deployment specifics. In the event of mass entry of objects created or sent in this manner into the atmosphere, meteor observation systems worldwide would likely detect unusual patterns in bolide activity in meteor streams. Would there be many coincidences between this and events related to suspected reconnaissance operations? It is quite possible that some collisions or close approaches with asteroids in mid-September could be interpreted as part of coordinated intelligence activities rather than random natural phenomena. This hypothesis is based on the fact that during that period, several asteroid collisions or flybys occurred, attracting significant media and public attention. At the same time, unusual behavior among space objects was observed, which at first glance might seem coincidental. However, it is important to remember that asteroid collisions and approaches to Earth are fairly regular phenomena that occur throughout the year. Most such events go unnoticed by the public unless they attract special media interest or are accompanied by unusual phenomena. It is likely that in September, there was a clustering of asteroid objects, primarily explained by improved detection capabilities and increased public awareness and attention to space. This does not necessarily mean that asteroid activity truly increased. Rather, thanks to modern technologies and more thorough observation, we are now noticing more such events. Overall, the increase in the number of registered space objects near Earth indicates the development and improvement of monitoring and detection systems, rather than a real rise in the number of hazardous asteroids. Regarding the solar maximum expected in the 25th century, if a serious threat related to objects like trilathlus or any other celestial bodies within our solar system were to actually be detected, the alert systems designed for such cases would activate immediately and accurately. They would quickly relay all necessary information about the level of danger to relevant national and international authorities to ensure timely response and preparation for possible consequences. The Center for Small Planet and Near-Earth Object Observation coordinates global efforts to continuously track potentially hazardous objects, while the Reactive Motion Laboratory, which studies near-Earth objects, maintains continuous and automated monitoring systems that enable the prompt detection of any changes in the movement and physical state of these bodies. The European Space Agency employs parallel data analysis and verification systems, providing independent checks of trajectories and collision probabilities, thereby eliminating errors and misunderstandings. All these international networks and monitoring systems guarantee that any real threats related to space objects will be identified at the earliest stage and officially reported to competent authorities so they can take necessary measures. At the same time, all information about potential danger remains strictly confidential to the public to prevent panic and misinterpretation. In modern society, there is a tendency to perceive apocalyptic and end-of-world scenarios as highly dramatic, often exceeding their objective probability. This is especially evident when it comes to phenomena that challenge conventional understanding of space or are associated with objects beyond our immediate observation zone. Psychological mechanisms and cognitive biases, similar to those that create the allure of conspiracy theories, make it possible for threats from unknown sources to be perceived as emotionally intense. Anxiety, in turn, is a natural human reaction to uncertainty and potential dangers. However, the situation with the object designated as trilathlus offers numerous confirmations that limit the likelihood of its danger. The trajectory of this object keeps it at a sufficient distance from all planets, and its physical characteristics fall within ranges explainable by natural processes, allowing us to assume its origin from cosmic phenomena rather than from hypothetical technologies or beings. The behavior of this object follows patterns characteristic of natural phenomena, even exotic ones, but still natural in origin. The most reasonable and scientifically justified approach is to continue observations with caution, while also paying attention to the unique opportunities that studying this interstellar visitor provides. It formed around another star and represents a valuable scientific discovery, regardless of whether its origin is entirely natural or conceals something more unusual. This interstellar object carries important information about processes occurring in space and conditions that cannot be reproduced or studied in terrestrial laboratories. The data collected about Tri-Atlas could significantly expand our knowledge of the formation and evolution of planetary systems in other star clusters. If the interpretation suggests a natural origin, we will gain new insights into how planets form and evolve beyond our solar system. However, if it turns out to be the result of activities by intelligent beings or technological civilizations, humanity will face a very complex challenge: learning to adapt to existence on a galactic scale, acknowledging the possibility of other intelligent life forms. In any case, even setting aside hypotheses about extraterrestrial activity and conspiracy theories, one aspect of the behavior of the Tri-Atlas object continues to surprise and undermine conventional scientific explanations. It captures the imagination and piques the interest of the general public, often in ways that go beyond rational understanding, sometimes creating a sense of mystery that cannot be fully unraveled. So, this is part 15. Final warning. Attention, alien. As the interstellar comet Atlas speeds toward its anticipated October visit to the inner solar system, it continues to attract special attention due to three key characteristics that make it unique and cause astonishment among astronomers. These features seem almost deliberately designed to challenge existing notions and compel scientists to view such objects in a new light. The first is the rapid and noticeable increase in brightness, which completely defies typical comet behavior models and deviated from predicted brightness curves as early as mid-September. Astronomical models based on decades of observations and well-established physical principles of ice sublimation under solar heat are considered among the most reliable tools for predicting comet brightness. When 3A Atlas, or Tri-Atlas, suddenly deviated beyond the expected trend line, it prompted a serious revision of conventional assumptions. These models had successfully explained the behavior of countless previous comets, and this deviation appeared quite significant in this case. This was not merely a minor deviation or a subtle anomaly. The difference was so pronounced that observers worldwide immediately noted that the comet appeared significantly brighter than what sky maps or predictive software had indicated. As a result, professional astronomers began recalculating their models, questioning whether they had overlooked any fundamental aspects of how interstellar objects react to solar heat, since all evidence pointed to the comet's behavior exceeding usual expectations. The second remarkable aspect is the extraordinary expansion of its atmosphere and its chemical composition. The coma, the gaseous envelope surrounding the comet's nucleus, which extends hundreds of thousands of kilometers into space during active sublimation of ice, displayed activity levels previously observed in only a few comets, raising serious questions about how a relatively small nucleus can sustain such extensive gas and dust production. Spectroscopic observations made with the James Webb Space Telescope revealed astonishing chemical ratios rarely seen in comets belonging to our solar system. These chemical signatures suggest that 3A Tassel formed under conditions fundamentally different from those that created comets within our system. The high content of carbon dioxide and the rapid expansion of the atmosphere point either to the presence of exotic volatile compounds or to more efficient sublimation processes than those predicted by existing models for objects at a distance roughly comparable to Jupiter's orbit. This chemical and physical profile indicates that this interstellar object likely originated in environments markedly different from those observed in our solar system, making it particularly enigmatic and intriguing for further study. Finally, the third and perhaps most astonishing aspect is the extreme polarization measurements of the light, which compelled specialists to seek unconventional explanations. During observations, the comet exhibited a minimum polarization value of about -2.5% at a phase angle of approximately 7 degrees, with an inversion point around 17 degrees. Such values have never been recorded in natural astronomical objects before and challenge conventional notions about the properties of dust particles that scatter light. Polarization measurements offer unique diagnostic capabilities, surpassing even brightness and spectroscopic analyses in their informativeness. They enable the determination of fundamental properties of dust particles, such as their size, shape, composition, and surface texture, as well as how these particles scatter light depending on their characteristics. This aspect is particularly important because it provides insight into the microscopic properties of dust particles. The fact that Comet Atlas produces polarization signatures that differ from any previously studied materials raises profound questions about its nature and origin. It presumably indicates either formation under conditions beyond those typical of our solar system or a composition including elements and materials that simply do not occur naturally within our system. However, these three characteristic features, an extraordinary increase in brightness, extreme expansion of the atmosphere, and unique polarization properties, combined with the visual effect of green glow and anti-tail geometry, create an impression reminiscent of something artificial. Naturally, this image prompts thoughts of a possible extraterrestrial origin of the object, especially because these features go beyond mere impressions confirmed by precise physical measurements, which cast serious doubt on their explainability within current scientific theories. Orbital calculations confirm that Comet 3ALS will remain at safe distances from Earth throughout its passage through the solar system. The closest approach is scheduled for December 19, when the comet will pass at a distance of 1 astronomical unit, ensuring no immediate physical threat to our planet regardless of its true nature or composition. At the same time, the encounter with Mars, planned for October 3, represents more of a valuable scientific opportunity than a dangerous collision scenario. This stage, along with the sequence of observations related to the approach to the Sun, creates a natural experiment that allows for the collection of information and scientific observation under the most transparent conditions. As of today, September 22, no new high-resolution images or photographs taken by major space telescopes have appeared in open databases, despite the ongoing evolution of the comet and the growing interest of the scientific community in documenting its unusual characteristics. The most detailed professional image remains the one obtained on August 27 by the Jenny-Sao Observatory, which is still considered the most informative to this day. This fact highlights the gap between amateur observations, which fill social media feeds and are often of low quality or insufficient accuracy, and the high-resolution data provided by major scientific institutions during significant astronomical events. This disparity is especially noticeable against the backdrop of the increasingly dramatic appearance of the comet throughout September. The period of connection with Earth that begins in late October will render Comet 3ALS virtually invisible from the surface of our planet precisely at the moment it reaches its peak activity near perihelion. This is a natural aspect of celestial mechanics, but it simultaneously creates conditions that pique the interest of conspiracy theorists, as well as pose real challenges for astronomers striving to document the object's behavior during its brightest and most active phase. Nevertheless, spacecraft scattered throughout the solar system will still have the opportunity to observe the comet during its fading activity. An orbital approach to Mars, scheduled for October 3, may be the last chance to obtain high-quality images before the comet disappears behind the Sun's glare. These observations are especially crucial for determining its true characteristics, as they could reveal the nature of such objects, including their composition, structure, and possible origin. What is the particular significance of such research for understanding the nature of comets? The answer to this question remains one of the most intriguing and relevant in modern astronomy. The way the scientific community analyzes and interprets the data collected during the third Atlas mission will set an important precedent for how humanity approaches potentially revolutionary discoveries in astronomy and space exploration in the future. Currently, we observe a unique combination of unusual features of this object, gaps in information, and a dramatic visual presentation, creating conditions that could test both the institutional reliability of scientific structures and the level of public trust in the authority of scientists. If the three-vertex object turns out to be a natural formation rather than something more unusual or artificial, its influence on the development of astronomy and the shaping of public consciousness cannot be underestimated today. This object has prompted scientists to reconsider existing assumptions about interstellar objects, demonstrating how quickly unusual observations can lead to broad theories about extraterrestrial civilizations and reconnaissance missions in space. It is important to remember that honest and objective analysis remains the main tool in this situation. So far, natural explanations, though stretched over time to accommodate all the unusual features of the third atlas, have not been definitively ruled out. It is quite possible that exotic volatile compounds, unusual internal structures, and formation conditions different from those typical of objects in our solar system could explain the observed anomalies without the need to assume artificial origin. However, the accumulated data raise serious doubts about conventional ideas of what natural interstellar bodies might look like and how they behave. This object is located at the frontier of current astronomical knowledge, exhibiting characteristics that either require significant extensions of existing theories or the consideration of alternative hypotheses capable of fundamentally rethinking our place in the universe. Modern scientific understanding suggests that the third atlas is either the most unusual natural object discovered in interstellar space or the first confirmed evidence that, on a galactic scale, advanced intelligence and technology exist, enabling reconnaissance missions over light-year distances. As this object approaches perihelion, that is, its closest point to the Sun, each new observation holds the potential to definitively resolve these questions. In the coming weeks, it will become clear whether the third atlas will enter textbooks as an exotic but natural formation expanding the boundaries of scientific knowledge, or whether it will confirm the hypothesis that humanity is not alone in the universe, and that advanced civilizations exist on a galactic scale, actively observing our actions from afar over light-year distances. The closer the object gets to the inner solar system, the more it appears alien, and this fact remains one of the deepest and most mysterious questions in modern astronomy. The question arises whether its external resemblance to extraterrestrial samples reflects genuine extraterrestrial origin or is the result of natural processes occurring under conditions we have never encountered before, which cause similarities to presumed alien forms. When the third atlas completes its flyby and exits conjunction with the Sun at the end of November, beginning of December, humanity will have a unique opportunity to finally determine whether this interstellar visitor conducted the most complex reconnaissance mission in galactic history or if it is a striking example of natural phenomena demonstrating the most dramatic manifestations of exotic processes observed in our universe. This discovery could completely overturn our understanding either of fundamental physical laws or of how widespread intelligence is in the universe. The new object, named Tri-Atlas, is turning into one of the most significant and astonishing astronomical formations ever detected in the skies of our planet. Its unique characteristics and scale evoke deep interest and pose new, challenging questions for scientists about the nature of the cosmos and its inhabitants. The entire history of scientific research shows that such discoveries have the power to radically change existing theories and perspectives, expand the horizons of human understanding, and open new fields for exploration. Therefore, the appearance of three atlas in the sky became an event that could forever change our perception of the universe we live in and the roles that consciousness plays within it.